Section 1 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne Spiegel. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 1, An Analysis of Matter, Part 1. When a child first opens his eyes on the world about him, a confusing array of experiences thrust themselves upon his notice. The clothes in which he is wrapped, the incomprehensible voice sounds that come to his ears, the ever-changing personalities of his environment. Everything is wonderful, strange, and fearsome because of its strangeness. So must the world of nature have seemed strange to early man, strange and terrifying. The sights and sounds of the forest, the wind rushing through the trees or lashing the rivers into foam, thunder and clouds and lightning, clear sun and quiet stars, all spoke to man in his earlier development impersonal voices. Each new object of sense constituted for him an object for suspicious investigation or superstitious fear. Familiarity may or may not breed contempt, but that it does induce a form of indifference is certain. When a leaf rustles in the forest today, the rational explanation of a breath of wind takes the place of the old-time fear of a wood demon. When a tidal wave rushes up a river, the modern knowledge of tides releases man from a blind terror. And this goes even further, for when a lightning flash strikes, the law of the association of ideas will lead the mind to correlate the incident with Benjamin Franklin and with the harnessing of the lightning to many everyday uses. Having passed the stage of superstitious wonder, man at once attempts to classify the phenomena of nature among those experiences of whose character already he feels himself sure. The earliest recorded beginnings of physical science were made, so far as history can testify, by the Chaldean astrologers. Their study of the stars, however, directed as it was rather to the prediction of individual and national destinies than to determining the real nature of the material universe, laid the groundwork for further study, but bequeathed little of practical importance in physics. No great names in science have been bequeathed to the world by Assyria or Chaldea. They may have furnished material for the imaginative genius of the Greeks, but the latter alone were capable of formulating into a system the vague wisdom of the Orient. As John Lord remarks, the East never gave valuable knowledge to the West. It gave the tendency to Egyptian mysticism, which in its turn tended to superstition. Instead of astronomy, it gave astrology. Instead of science, it gave magic, incantations, and dreams. The Chaldean and Assyrian civilizations, which gave birth to the astrology of the Magi, flourished and declined in the fertile valleys of the Tigris and Euphrates. Nearly 1,000 years before them, however, there had been developing in the fecund region of the Nile the people who produced the first of these marvelous pyramids, which remain today the greatest monuments of history. Some considerable knowledge of physics and the elementary application of machines the Egyptians must have possessed, or at least the builders of the pyramids, whoever they were. The stones are much larger than those used in architecture today. The columns of the Egyptian temples, still standing in ruins, are immense. Travelers look with astonishment and admiration at the gigantic structures whose walls, lintels, columns, and entablatures are formed of material cut in extraordinary dimensions. No scientific works remain to show how the ancient builders of Egypt managed to carry and put in place such large blocks of stone. Mural paintings, sculptures, and inscriptions are the only means of conveying such slight information as has been handed down to the present generation. It has been held by some students of antiquity that the pyramids were designed as institutions to embody cosmic discoveries. For example, that certain specific measurements of the structure bear a definite ratio to such matters as the exact length of the Earth's circumference and diameter, the length of an arc of meridian, and standard units of measure. Other theorists, with far more probability in their favor, believe the pyramids to have been constructed as the tombs of the great kings, whose names are graven in the interior and whose sarcophagi, with their mummies, are often found in the central chamber. Still others have declared that the pyramids were used for astronomical study. Whatever other purpose the pyramids may have served, they seem to have been little adapted for observatories. It is a matter of common knowledge that an object viewed through a roll of paper is better seen in detail than when looked at without such aid. Place a lens in either end of the roll, adjust the focus of the lenses, and a telescope is made. The eye takes in a great deal more than the mind perceives. In gazing at an object, especially at a distance, the detail of the object is obscured by the light reflected from hundreds of other objects in the neighborhood. The simple roll of paper overcomes this difficulty in exactly the same way that the ventilating passages, the so-called telescopes, of the pyramids might do. A star is visible in broad daylight when viewed through such a long, narrow passage as were these 9-inch telescopes of the pyramids. A fatal defect in this telescope thesis, however, is the fact that the earth revolves, and a star visible for a few seconds at the aperture of the passage would be lost almost immediately. In their astronomical observations, and in their arithmetical calculations, the Egyptians were inferior to the Chaldeans. They were familiar with the true meridian and the length of the sidereal year. They did not know the signs of the zodiac, however, nor are there any inscriptions of Egyptian origin such as are found on the Assyrian bricks, wherein appear the square and cubic multiplication tables and the 360 degrees of the circle. The Egyptian zodiac of the temple at Derdera is now known to be a production comparatively modern in origin, even showing Greek influence. The Hellenic philosophers made the first definite classification of elements, asserting that earth, air, fire, and water were the 4 indivisible substances out of which the whole world was made up. They knew a god of the water, Poseidon, Neptune, a god of earth, Antaeus, a god of fire, Pluto, while each of the 4 winds was a deity. However simple and clear such a division might seem, modern science has proved that each of these supposed elements is divisible into several elementary substances. Thus, ordinary water, for instance, is known to be compounded of oxygen and hydrogen. Air is a mixture of nitrogen, oxygen, carbonic acid gas, and a number of other elements, more recently isolated, among which helium is of especial interest. And so numerous are the component parts of Earth that it seems most strange how it could ever have been conceived as an element at all. Despite all errors in explaining the phenomena of nature, however, Greece must be credited with having made the first real beginning of that classified knowledge out of which has developed the natural science of modern times. Thales, the founder of the Ionic school of philosophers, is reported to have determined the course of the sun from solstice to solstice, and to have calculated eclipses. He attributed an eclipse of the moon to the interposition of the earth between the sun and moon, and an eclipse of the sun to the interposition of the moon between the sun and earth, and thus taught the rotundity of the earth, sun, and moon. He also held that water is the principle of all things, a somewhat egregious error from the modern point of view. As soon as 280 years before the present era, Aristarchus, Hippocrates, and Galen made many scientific advances, but physics was not yet strongly differentiated from its attendant sciences. The mantle of the Greek philosophers was caught up by Pliny, who perished in the eruption of Vesuvius in 23 A.D. His natural history, in 37 books, treats of everything in the natural world, of the heavenly bodies, of the elements, of thunder and lightning, of the winds and seasons. Like nearly all the Greek and Roman philosophers, however, and many great theorists of later date, Pliny contented himself with theorizing. In mathematics, metaphysics, literature, and art, the Greeks displayed wonderful creative genius, but in natural science they achieved comparatively little. It would not be correct to say that they possessed little or no aptitude for observing natural phenomena, says Florian Chiori in his History of Physics, but it is true that, as a rule, they were ignorant of the art of experimentation, and that many of their physical speculations were vague, trifling, and worthless. As compared with the vast amount of theoretical deductions about nature, the number of experiments known to have been performed by the Greeks is surprisingly small. Little or no attempt was made to verify speculation by experimental evidence. As a conspicuous example of misty philosophizing, we give Aristotle's proof that the world is perfect. The bodies of which the world is composed are solids, and therefore have dimensions. Now 3 is the most perfect number. It is the first of numbers, for of 1 we do not speak as a number, of 2 we say both, but 3 is the first number, of which we say all. Moreover, it has a beginning, a middle, and an end. Mechanical subjects are treated in the writings of Aristotle. The great peripatetic had grasped the notion of the parallelogram of forces for the special case of the rectangle. He attempted the theory of the lever, stating that a force at a greater distance from the fulcrum moves a weight more easily because it describes a greater circle. Aristotle's views of falling bodies are very far from the truth. Nevertheless, they demand attention for the reason that during the Middle Ages and Renaissance, his authority was so great that they play an important role in scientific thought. He says, that body is heavier than another which, in an equal bulk, moves downward quicker. In another place, he teaches that bodies fall quicker in exact proportion to their weight. No statement could be further from the truth. A modern writer endeavors to exonerate Aristotle as a physicist. If he could have had any modern instrument of observation, such as the telescope or microscope, or even the thermometer or barometer, placed in his hands, how swiftly would he have used such an advantage? But in the case of falling bodies, the experiment was within his reach. If it had only occurred to him, while walking up and down the paths near his school in Athens, to pick up 2 stones of unequal weight and drop them together, he could easily have seen that the one of, say, 10 times the weight did not descend 10 times faster. Immeasurably superior to Aristotle as a student of mechanics is Archimedes, 287 to 212 BC. He is the true originator of mechanics as a science. To him belongs the honor of enunciating the theory of the center of gravity, centroid, and of the lever. In his Equiponderance of Planes, he starts with the axiom that equal weights acting at equal distances on opposite sides of a pivot are in equilibrium, and then endeavors to establish the principle that in the lever unequal weights are in equilibrium only when they are inversely proportional to the arms from which they are suspended. His appreciation of its efficiency is echoed in the exclamation attributed to him, "Give me where I may stand and I will move the world." While the Equiponderance treats of solids, or the equilibrium of solids, the book on floating bodies treats of hydrostatics. The attention of Archimedes was first drawn to the subject of specific gravity when King Hieron asked him to test whether a crown, professed by the maker to be pure gold, was not alloyed with silver. The story goes that the philosopher was in a bath when the true method of solution flashed on his mind. He immediately leapt from the bath and ran home, shouting, "I have found it!" To solve the problem, he took a piece of gold and a piece of silver, each weighing the same as the crown, the piece of silver being almost twice the size of the gold. He then determined the volume of water displaced by the gold, the silver, and the crown respectively, and from that calculated the amount of gold and silver in the crown. The proportion of greater displacement in the crown, above the piece of pure gold, showed the extent of the alloy. In his Floating Bodies, Archimedes established the important principle, known by his name, that the loss of weight of a body submerged in water is equal to the weight of the water displaced, and that a floating body displaces its own weight of water. Since the days of Archimedes, able minds have drawn erroneous conclusions on liquid pressure. The expression hydrostatic paradox indicates the slippery nature of the subject. all the more must we admire the clearness of conception and almost perfect logical rigor which characterize the investigations of Archimedes. Archimedes is said to have shown wonderful inventive genius in various mechanical inventions. It is reported that he astonished the court of Hieron by moving heavy ships by aid of a collection of pulleys. To him is ascribed the invention of water engines and the endless screw of Archimedes, which was used to drain the holds of ships. This genius, the greatest scientist before Galileo, perished in the siege of Syracuse by the Romans, 212 BC. About a century after Archimedes, there flourished Ctesibius and his pupil Heron, both of Alexandria. They contributed little to the advancement of theoretical investigation, but displayed wonderful mechanical ingenuity. The force pump is probably the invention of Ctesibius. The suction pump is older and was known in the time of Aristotle. According to Vitruvius, Ctesibius designed the ancient fire engine, consisting of the combination of two force pumps spraying alternately. The machine had no air chamber and therefore could not produce a steady stream. Heron describes the fire engine in his Pneumatica. During the Middle Ages, the fire engine was unknown. It is said to have been first used in Augsburg in 1518. Ctesibius is credited with the invention of the hydraulic organ, the water clock, and the catapult. Heron showed the earliest application of steam as a motive power in his toy called the eolipile. It was the forerunner of Barker's water mill and the modern turbine. Heron wrote an important book on geodesy called Dioptra. The Greeks invented the hydrometer probably in the 4th century A.D. There appears to be no good evidence for attributing its origin to Archimedes. The hydrometer, a device in common use today for measuring the densities of water, milk, and acids, is described in full by Bishop Synesius in a letter to Hypatia. It consisted of a hollow graduated tin cylinder weighted below. Immersed in a liquid, the depth to which it sank constituted a measure of the relative weight or density of that liquid. It was first used in medicine to determine the quality of drinking water, hard water being at that time considered unwholesome. According to Desaguliers, it was used for this purpose as late as the 18th century. Since in such distant days, and with theories so diverse from those of modern times, the study of matter and of its properties began, the question arises whether the initial problem has yet been solved. Theories have been multiplied, modified, rejected, confirmed. Through the centuries, the evidence of experiment has accumulated. Much has been learned of the nature and behavior of matter under varying conditions, but the complexity of the problem has become more evident the further it is studied, and the complete answer is not yet. The world is rife today with stores of knowledge undreamed of a few centuries ago. But since every addition to the sum of information brings with it a new series of problems, human reason halts before the attainment of a conclusive knowledge as to the real essence of that which it calls matter. The Greek-Roman Asclepiades conceived matter to consist of extremely small but still divisible and fragile, formless, and mutable collections of atoms, cognizable indeed by the understanding but not by the senses. These atoms originally moved about uncontrolled in a general vacuum and burst in pieces through accidental collisions. By union of the finest fragments thus engendered, the leptomeres originate the visible bodies, whose differences of form and varying peculiarities have their foundation in the different association of the leptomeres into different bodies. In a quaint series of inquiries by John Abercrombie, The Investigation of Truth, published in Edinburgh 3/4 of a century ago, matter is defined as a name which we apply to a certain combination of properties or to certain substances which are solid, extended, and divisible, and which are known to us only by these properties. Francis Bacon, the wisest, brightest, meanest of mankind, as the Pope styled him, conceived of matter as made up of two tribes of things, the sulphureous and the mercurial, which, he says, seem vastly extensive so as to enter and occupy the whole material world. Sir Isaac Newton regarded matter as the coexistence of the smallest particles which are themselves extended and material, and which, through a power whose nature he did not further analyze, hang together. Newton, therefore, adhered to the atomistic school, of which the Greek Democritus of Abdera was the great classical expositor. He did not believe in the infinite subdivisibility of matter. In his Treatise on Light, the great philosopher concludes that it seems extremely probable that the Creator so formed matter that its primary particles, out of which all possible bodies afterwards arose, was firm, hard, impenetrable, and movable. These particles, therefore, could not through any known force be divided, hence all bodies composed of these minute granules possessed interstices, because otherwise their parts could not be separated from one another, and matter was therefore divisible only until its atoms were reached. Moreover, these primary particles possessed not only a power which subjected them to certain immutable laws of motion, but also the capacity of being set in motion through other influencing causes, for example, gravity, fermentation, and cohesion. In accordance with these premises, Newton justly combated the theory of his great contemporary, Cartesius, that matter occupied all space. His excellent development of the idea of the resistance of a medium led to conclusions which inevitably contradicted Cartesius's theory of filled space. In such a compact mass as the latter theory assumed, a mass which would be absolutely impenetrable, all motion must find an unlimited resistance. Cartesius assumed, it is true, that this subtle matter was so finely divided as scarcely to exist at all, but Newton showed that this was only empty assertion. He based his opposition to the theory on the ground that the smallest subdividing of matter would not appreciably diminish the resistance which filled space would present to a moving body, especially since the body in motion would enforcedly have a density not greatly dissimilar to the resisting medium. Therefore, he argued, a medium wherein bodies move without perceptible retardation must be immensely more attenuated than the bodies themselves. On the other hand, a cannonball projected into the filled space of Cartesius, be that medium ever so finely divided, would lose more than half its motion before it had moved a distance of thrice its diameter. It would be impossible on this supposition for a man to move from a given spot, much less the heavenly bodies, whose courses show no perceptible retardation, as would inevitably be the case were they to be advancing through an absolutely dense medium. The belief in filled space did not originate with Cartesius. It is rather remarkable that the two thinkers who of all men in history most powerfully have swayed philosophic thought, Aristotle and Kant, were both exponents of the doctrine that space is continuously filled. The great ancient expositor of the atomic theory was Democritus of Abdera. He taught that the world consists of empty space and an infinite number of indivisible, invisibly small atoms. Bodies appear and disappear only by the union and separation of atoms. Even the phenomena of sensation and thought he affirmed to be the result of their combination. Newton's belief in the granular or atomic nature of matter has been abundantly upheld by the evidence of modern research. It is true that the chemical atom is no longer considered the ultimate unit of material structure. One brilliant writer on this subject has recently advanced a series of exhaustive arguments in favor of the Newtonian thesis. He points out, however, that it is by no means an impossible conclusion that matter in the form of interstellar ether may have properties quite different from those which are observed of matter in the mass. It has been remarked above that Newton did not attempt to describe the nature of force. He merely assumed its existence as evidenced by the behavior of matter. This was natural, for reason must commence with an assumption and arrives at conclusions based simply upon the evidence of the physical senses. While force is generally conceived rather as an object of thought than of sense, yet it should not be forgotten that force has just as real an existence as matter. End of section 1. Section 2 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 1, An Analysis of Matter, Part 2. Many and various definitions of matter have been made in the course of scientific history. It has been described, for example, as that which occupies space, or as the receptacle of energy, or again as the permanent possibility of sensation. All these may be brought under one of two general heads. Either matter must be defined, as Bacon defined it, in terms of its properties, or it must be defined in terms of its coexistent phenomenon, force. It is clear that the physical world may be comprehended within the limits of these two notions, force and matter. Force is that which acts upon matter. Matter is that by which man apprehends force. Force is by no means such a vague and various thing as is sometimes supposed. There is today a very general tendency among scientific writers to endeavor to reduce all force to a single underlying principle. The establishment of the theory of the conservation of energy, the ready transmutation in everyday experience of various forms of force, such as the conversion of sound into electricity and of the latter into heat, light, motion, or chemical energy, the advances in the study of radioactivity, and the general acceptance of the kinetic theory of gases, all point to an ultimate unification under some one great principle of the various forms of force. Gravity alone seems incapable of classification with other forces, and this is due to its independence of any quality but mass. Temperature will affect the conductivity of an electric wire. Solution is greatly influenced by pressure. Light has a determinative effect upon physical life, as upon many chemical reactions. But gravity is not affected by these conditions of temperature or of the intervening medium. Its nature is utterly unknown. Electricity has long been held to be a form of force. It acts upon matter to change its condition. It is not an object of sense in a current-carrying wire or a charged Leyden jar. It seems to be typical of what is popularly understood by the name force. Yet the study of the cathode rays by Sir William Crookes and his great co-workers in this field of research, Roentgen, Hertz, Rutherford, and others whose names are perhaps even more familiar, has made it apparent that something closely resembling material particles are actually discharged from the cathode or negative pole of an electric conductor when the current passes. So strong, indeed, is the accepted belief that the nature of electricity is material rather than dynamic, that a distinguished American chemist recently formulated the thesis that electricity is one of the elements. To obtain a clear understanding of the most modern theories with regard to the nature of matter, a brief description of the apparatus used by investigators is inevitable. Imagine an electric bulb or oval vessel of glass. In this are placed two electrodes, which may be either metallic points or bulbs, or, in short, any poles separated by smaller or greater intervals and charged with electricity. Their electrification will be maintained, for example, by placing them in connection with the terminals of an electric current of high voltage. A short tube provided with a stopcock allows the bulb to be exhausted of air. When the electric tension passes a certain limit, a current is established. If the vacuum is maintained at something less than 1,000th of an atmosphere, this current appears as a soft, rose-colored glow passing within the bulb from the positive to the negative pole. Sir William Crookes pushed the exhaustion of air in his experiments to a prodigious degree, the pressure being only 1/1,000,000th of an atmosphere. Concerning Crookes' experiments, M.A. Daster writes, "The English scientist claimed that when exhausted to this point, the residue no longer has the properties of ordinary gas. According to him, it is hypergas, as different from the true gaseous state as the latter is from the liquid state, and forming a fourth condition of matter, following the solid, the liquid, and the gas proper. This he called radiant matter." Crookes desired to determine the nature of this fourth state of matter. In reality, the gas, rarefied to the 1,000,000th of an atmosphere, has not acquired, by this fact alone, an entirely new character. but it has acquired it most certainly when electrification is added to the rarefaction, and it is then that it constitutes the emanation or the cathode ray. The vacuum must not be pushed too far. If one goes beyond the millionth of an atmosphere, and the perfection of mechanism allows going much further than that, the gaseous residue cannot be electrified. Electricity will not pass through. There is no longer a current. The electric force is incapable of penetrating absolute vacuum. The importance of this principle is very great from the theoretical point of view. It furnishes, in fact, a new test for matter. But in Crookes's tube, in which the vacuum has been pushed to 1/1,000,000th, the current behaves itself rather differently from what it does in the tubes where the rarefaction is less. The point of the current has lost much of its brilliancy. It no longer appears as an uncertain glow, wavering, striated, of a hue intermediate between rose and violet. All the remainder of the interior of the bulb now remains dark. The electricity passes as before between the positive electrode and the cathode or negative pole. The principal flow has been joined by a secondary one. From all points of the tube, the positive currents are directed towards the cathode and go to reinforce the principal current. These positive charges, which descend from all points of the exterior, form the counterpart of the negative charges, which can be seen fixed in the cathode rays. Their existence, their development, their circulation result in consequence from the existence, the development, and the inverse circulation of the negative electricity that carries with it the cathode ray. Such is the cathode afflux. It is composed of the current directed toward the positive electrode and of secondary currents directed from all parts of the recipient toward the cathode. This cathode afflux has, besides, the character and the properties that physicists and chemists attribute to the electric current. It touches directly the cathode. The afflux, however, is in fact perfectly distinct in every respect from the cathode radiation which follows it. The latter is formed of a pencil of rays perpendicular to the surface of the cathode. It traverses the tube in a perfectly straight line without being disturbed by the rays flowing toward the cathode in an opposite direction, of which we have just been speaking. It passes by them and through them unchecked. This new pencil, implanted perpendicularly on the cathode, is not luminous. It is not directly visible. It forms a dark spot in the Crookes tube. It would entirely escape observation if it did not excite a peculiar fluorescence opposite to the cathode at the points where it meets the sides of the tube. The material of the glass becomes illuminated at these points and presents a luminous, brilliant spot of green color. Crookes conceived the idea of arranging in the interior of the tube, in the path of the pencil rays, between the cathode and the wall, a cross of aluminum. He then saw outlined against the clear fluorescent background the exact silhouette of the cross. If the cathode is a mirror with spherical concave surface, the perpendicular lines at the surface form a conical pencil and converge toward a focus. The effects peculiar to cathode rays are magnified by this concentration in the same manner that the effects of luminous rays are increased in the focus of a lens. In this manner, Crookes was able to show the heating action of his supposed radiant matter, that is to say, of cathode rays. He succeeded in fusing, at one of these foci, not only glass, but a wire of iridium platinum, an operation which requires a temperature of more than 2,000 degrees. When the cathode rays are reflected from a sheet of platinum within the tube, the marvelous phenomena of X-rays, or Roentgen rays, are produced. These rays are different in character from the cathode rays in that they pass readily through wood, flesh, cardboard, and even thin sheets of metal. Their serviceability in locating and determining the nature of a fracture in a bone is too well known to need comment. The cathode projectile does not depend upon the nature of the cathode. It has been proved to be composed of hydrogen. It has its origin necessarily in the breaking up of an atom of hydrogen. Villard showed that the cathode rays exhibit the spectrum of hydrogen, and if every trace of this gas is removed, the cathode emission is suddenly suppressed. Hydrogen, observes M. d'Astre, in the article quoted above, instead of being the final expression of simplicity and of lightness, as chemists believe, appears to be a quite complex edifice and rather heavy, since the current of the Crookes tube removes from the stones which represent it but the 1,000th part of its mass. These stones are the fragments of atoms, or the atomic corpuscles of J. Thomson. The atom is no longer indivisible. The infinitesimal mass of an atom is a fact sometimes lost sight of in discussing the constitution of matter. It has been estimated from experimentation with colored solutions of a known concentrate that the weight of an atom of hydrogen is less than 19.008 times 10 to the negative 13th ounce, and its diameter is less than 2 times 10 to the negative 9th inches. Following this line of inquiry as to the ultimate constitution of matter, there has recently appeared an article by Dr. W. D. Horn, which reads in part as follows. From considerations based partly on very elaborate mathematical calculations, it is now maintained that matter is composed of electricity and nothing else. Electricity here is not considered as a form of energy any more than water is a form of energy, but as a vehicle of energy, which can be moved from place to place and whose energy must be in the form of motion or of strain. In motion, it constitutes current and magnetism. Under strain, it constitutes charge, and in vibration, it constitutes light. Continuing, the same writer says, Sir Oliver Lodge describes the atom of matter as constituted of an individualized mass of positive electricity diffused uniformly over a space the size of an atom, perhaps spherical in shape, and about 1/200,000,000th of an inch in diameter. Throughout this small spherical shape, some 800 minute particles of negative electricity, all exactly alike, are supposed to be scattered, flying vigorously about, each repelling every other, and yet all contained within their orbits by the mass of positive electricity. The positive electricity is very much attenuated and constitutes perhaps only about 1% of the mass of the atom, while the negative electrons are correspondingly dense and so inconceivably small that the 800 are less crowded in their atom than are the planets in the solar system. Atoms of different kinds of matter are supposed to be constructed in the same general manner and of the same kind of electrons, but the number of electrons in an atom are proportional to the atomic weight of the element. Thus oxygen would have 16 times as many electrons in its atom as has hydrogen. When the crowding becomes excessive, as in the very heavy atoms of uranium, the heaviest substance known, thorium and radium, being atomic weights well over 200, the atoms become radioactive, probably due to numerous collisions between the electrons, some of which are being constantly shot away. This perspicuous summary of the so-called electron theory is highly suggestive of the fundamental unity of force and matter. Moreover, the electron theory seems, so far, most in accord with the results of recent investigation into the physical basis of the material universe. Curiously enough, the medieval alchemists who, next after the Greeks, attempted to establish an orderly classification of the elements actually anticipated one of the most modern theories regarding the properties of matter. They believed in the philosopher's stone, which, if it could but be discovered, would make possible the transformation of any or all of the baser metals into gold. Recent investigation has shown that something like a true philosopher's stone actually exists and is known in the world today. It is a well-accepted belief that the Earth in its passage through space gathers up constantly minute quantities of gas helium, so called because its spectrum was first found in the analysis of light from the sun and before the discovery of the element in the terrestrial atmosphere. The theory has lately been advanced that under the influence of helium, the nobler metals, silver and gold, are slowly disintegrating and their electrons recombining through immense periods of time to form the baser metals, iron, copper, tin, zinc, etc. In a discussion of modern views on the matter, Sir Oliver Lodge observed that the facts recorded in connection with the study of radioactivity constituted a phenomenon quite new in the history of the world. No one, he says, hitherto has observed the transition from one form of matter to another, though throughout the Middle Ages such a transmutation was looked for. The evolution of matter, likewise, has been suspected by a few chemists of genius. It was perceived, on the strength of Mendeleev's law, the periodic law, that the elements form a kind of family or a related series, and it was surmised that possibly the barriers between one species and the next were not absolutely infrangible, but that temporary transitional forms might occur. All this was speculation, but here in radioactive matter the process appears to be going on before our eyes. End of Chapter 1. Section 3 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 2, The Properties of Matter, Part 1. The foregoing brief inquiry into the essence of matter leads naturally to a consideration of its properties. Of these properties, the first and foremost is that of weight. The term ponderable matter has long been used to distinguish matter in the mass, whereby is plainly indicated the most fundamental property of matter as such. Even in ancient times it was realized that any consideration of matter would deal primarily with questions bearing a definite relation to weight, and the development of the knowledge of the laws concerning the attraction of bodies for each other is closely allied to the inner history of physics. In that renaissance of learning and thought which succeeded the gloom of the Dark Ages in Europe, arose many great lights of science. Copernicus outlined the system which subsequently became known by his name. Kepler grappled with the problem of determining the paths of the planets. Galileo laid the foundation of experimental science. The belief in the Earth as the center of the universe was then overthrown. Copernicus taught that the Earth was not flat but spherical, that it rotated on its axis and revolved around the sun, that seasons are due to the inclination of the Earth's axis. He defined gravity as nothing other than a certain natural appetite innate in the parts of matter by the divine providence of the artificer of the universe, so that they assemble themselves in an exact unity, combining in the form of globes. The marvelous mathematical insight of Kepler proved the accuracy of the Copernican theory, and he demonstrated that the elliptical orbit of Mars would accord exactly with this theory and with no other. The famous experiments of Galileo with falling bodies constituted as clear a proof of a principle as ever man has made. The young investigator was the first, actually, to try out the assertion of Aristotle that falling bodies would descend with a velocity proportionate to their weight. A stone weighing 10 pounds would fall 10 times as fast as a stone weighing but 1 pound. Galileo did not believe this, and having found from experimentation that it was not so, openly proclaimed his conviction that Aristotle was wrong. His opinions were hotly opposed by the learned professors of the University of Pisa. By agreement, the case was put to the test, and from the top of the Leaning Tower of Pisa, Galileo allowed a small cannonball and a large bomb to drop together. The multitude saw the balls start together, fall together, and heard them strike the ground together. Some were convinced, others returned to their rooms, consulted Aristotle, and, distrusting the evidence of their senses, declared continued allegiance to his doctrine. Galileo then experimented with a polished brass ball rolling down a smooth incline in order to establish the ratio between the distance traversed and the time of falling. Clocks did not exist in his day, and he resorted to a very interesting and ingenious device for measuring the time elapsed during the progress of this experiment. Attaching a small spigot to the bottom of a water pail, he caught the escaping water and measured its weight, comparing the increase of weight with the distance traversed by the ball. From these experiments, he found the distance to increase very closely to the square of the time. Galileo's reflections had brought him to the confident belief that Copernicus's theory of the solar system was as true as that of Aristotle was false. He taught and wrote much to support this doctrine, and by his sarcastic raillery against the narrow prejudice of his contemporaries, incurred the enmity of many. As an old man of nearly 70, he published a brilliant defense of the Copernican system, which aroused such fierce antagonism that he was forced publicly to abjure and to curse his detestable heresy, viz., that the earth moves round the sun. His "E pour si mouve," but it does move, uttered as he came forth from his trial, has become historic. The extraordinarily active mind of this investigator seemed ever to be discovering new and interesting phenomena. It is said of Galileo that while he was praying in the cathedral at Pisa, his attention was drawn to the lamps which had been lighted and left irregularly swinging above the altar. His mind at once set off on the question as to whether the period of a pendulum would vary exactly with the amplitude, width of its vibration. He timed one of the swinging lamps by his pulse and found that the period of vibration was exactly the same, no matter whether the pendulum was swinging violently or dying down to rest. Later experiments confirmed the conclusion and led likewise to the discovery that the length only of a pendulum affected the time of its oscillation. A slender wire with a small steel ball for a bob swings to and fro in exactly the same period as a heavy iron bar whose center of gravity is at an equal distance from the point of suspension. Galileo found out that the swing of a pendulum varied as the square root of its length. Thus, a pendulum 4 feet long will vibrate half as fast as a pendulum a foot long. The pendulum is used today in experimenting upon the attraction due to gravity in different parts of the earth, and by its help the flattening towards the poles of the curved surface of the earth can be exactly determined. The attraction due to gravity varies inversely as the square of the distance from the center of the earth. Thus, a pendulum which possesses at New York a length of 39.1 inches will vibrate once every second at that point of the Earth's surface. As it moves toward the poles, the pendulum vibrates more rapidly. If the change of location is made in the direction of the equator, the vibration is slower. This for the reason that the pull of the Earth is less, since at the equator the pendulum is farther from the center of gravity of the Earth. Of the same character was the famous Foucault experiment to show the rotation of the Earth. On this experiment, it was shown that a pendulum at rest, if of sufficient length, would oscillate owing to the motion of the Earth, the various factors operating throughout the pendulum, each point of which was at a varying distance from the center of the Earth. The discovery that a pendulum of fixed length always vibrated in the same period led naturally to the invention of the pendulum clock. For this invention, credit has been ascribed to several unknown men, but it is probable that the honors should be divided between Galileo and his famous Dutch contemporary, Christian Huygens. The significance of this invention in the history of physical science is great indeed, when account is taken of the innumerable forms of experimentation which have been reduced by its aid to exact sciences. While Galileo, Kepler, and Copernicus had completely overthrown the ancient theory of Aristotle that the Earth is the center of the universe, and had mathematically proved that the solar system revolves around the sun as a center, they did not show the why of these new and startling discoveries. The puzzle stared philosophers in the face. What is it that causes the planets to move in their orbits? To this question, Descartes proposed the novel and striking explanation of a series of whirls or vortices. All space, he argued, was filled with a fluid, the parts of which, acting on each other, caused circular motion. Thus, the fluid was formed into a multitude of vortices of varying density and size. A huge vortex around the sun carries with it the Earth and all the other planets. Each planet in the same way is the center of a vortex of its own, and draws bodies to itself in much the same way that a log of wood is drawn into the center of a whirlpool. Cohesion between the different parts of a body, he explained, in the same manner as the result of infinitesimally small vortices. Unsatisfactory as this vortex theory seemed, and quite out of accord with the laws which Kepler's intellect had formulated, yet the weight of authority lent to it by the great name of Descartes resulted in its persistence as a generally accepted theory until the middle of the 18th century. Greatest of all natural scientists of this or any time, and the first to formulate completely and finally the laws of matter, was the great English mathematician and physicist, prince of philosophers, Sir Isaac Newton. It was reserved for his genius to show why the apple which falls from a tree falls down to the earth and not up to the clouds, how the earth, This infinitesimal point in space does not rush headlong into the sun or fly off at a tangent into the void beyond the solar system. Why the wave rebounds from the cliff, and why the pendulum swings to and fro. Newton's law of universal gravitation is the catechism of astronomy. His 3 laws of motion have become the basis of physics and the bedrock of the science of mechanics. That which is known as Newton's law of universal gravitation is in brief as follows. Any 2 bodies in the universe attract each other with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. The term mass, as used here and generally in a physical discussion, refers to a constant quality of weight in a body. As a pendulum varies in its swing at different points upon the Earth's surface, so a pound of iron at the equator will weigh less than a pound in Greenland. The influence of the Earth acts upon all bodies exactly as though its whole mass were concentrated at the center. Hence, a pound weight at the surface of the Earth, 4,000 miles from its center, would weigh, according to Newton's law of gravitation, heavier and heavier as it approached the center. Similarly, if the weight were carried away to a distance of, say, 4,000 miles from the surface of the Earth, it would weigh only 1/4 as much as it did at the surface, since it is twice as far away from the Earth's center. Or again, a body which would weigh 1,000 ounces at sea level would weigh about 998 ounces at the top of a mountain 4 miles high. Nevertheless, the mass of the body, i.e. its power to attract other bodies, would remain the same. An athlete who weighs 150 pounds can leap at the surface of the Earth over a bar 6 feet high. Carry him to the moon, and the same muscular effort would carry him at a bound over an obstacle 40 feet high, and his descent on the other side would be comparatively slow. The mass of the moon being about 1/7 that of the Earth, the same effort would accomplish 7 times as much work, since the resistance to be overcome would be the mass of the man multiplied by the mass of the moon. If it is true that the Earth attracts the moon, it is equally true that the moon attracts the Earth, as is shown by the tidal wave which follows the moon in its apparent revolution around the Earth, and this attraction is equal to the product of the masses of the moon and the Earth. Were the moon brought to a point 1/4 as distant as its present path around the Earth, its speed of revolution would be increased enormously, and its influence on the water surface of the Earth would raise resistless mountain tides, sweeping the land from east to west as the Earth revolved. Newton's famous apple, detached from the tree, leaps to meet the Earth, but it is equally true that the Earth leaps up to meet the apple. The relatively great disturbance in the position of the apple is due only to the vastly greater mass of the Earth. Newton's great laws of motion were stated thus. 1. Every body continues in its state of rest or uniform motion in a straight line unless impelled by external force to change that state. Standing on a moving car, the passenger is thrown violently forward when the car comes to a sudden stop, and backward when the car starts. He tends in each case to continue in the previous state, whether that were one of rest or motion. Water flies from whirling grindstone, mud from the spinning wheels of a rapidly driven motor car. At each instant, the world is rushing forward in a straight line through space, but at the same instant, the prodigious mass of the sun is acting upon it to pull the Earth into itself. Between these 2 forces, the Earth is impelled in an almost circular orbit around the sun. The centrifugal force is exactly balanced by the centripetal force, which acts upon the Earth exactly as 2 bits of floating wood in a quiet pond will come together, or as a vessel drifts to meet an iceberg. The resultant of the 2 forces acting upon the Earth may be apparent from the following diagram. Suppose the short side of the oblong, ES, represents the direction and extent of the sun's attraction for the Earth. Then if ET, the long side, represents the tendency to fly off at a tangent, the resultant motion will evidently be between these 2. Aristotle knew that if 2 such forces were acting at right angles on a body, the resultant motion would be represented by the diagonal of a rectangle of which the forces were sides. The line EO, representing a part of the Earth's path around the sun, appears as a straight line only because it is taken as a very small arc of an enormous circumference. 2. rate of change of momentum is proportional to the force acting and takes place in the direction in which the force acts. On a steep slope, gravity impels a body more than on a gentle incline. A sled will gather headway faster on an abrupt descent. A car will travel faster with a greater current through the motor. Other things being equal, a steamer with 2 propellers making 5,000 revolutions per minute would travel twice as fast as the same steamer under 1 propeller. Here, however, the resistance of the water at the bows, which increases for high speeds very nearly as the cube of the speed, and the whirl of water astern, which reduces the perfect efficiency of the screw, would have to be taken account of. 3. Newton stated his third law as thus: to every action there is an equal and opposite reaction. This does not mean that a bouncing ball will go on bouncing forever. Everyone knows that it will not. It does not mean that the kick of a gun is exactly equal to the force with which the bullet leaves the muzzle, or that a pendulum will swing up on one side exactly as far as it swung down on the other. In all these cases, the energy expended is equal to the work accomplished, but in each case, a part of the energy is expended in overcoming resistance and doing work which cannot be seen. A tennis ball dropped to the floor will rebound about 3/4 as high as the point from which it fell. Part of the energy of compression was expended in the flattening of the cover of the ball, and part in overcoming the resistance of the air. The kick of the gun is taken up by a padding of clothes. The pendulum is retarded by friction. The most elastic solid in the world is steel. To the majority of people it would appear that some such resilient material as rubber or ivory is the most elastic. This is not the case. Within a low range of strains, it is true that rubber has very great elasticity. The tendency of its molecules to resume their former positions after being distended is very great. Beyond the limit of this tension, however, the rubber stiffens, the molecules fall asunder, and the band breaks. A steel piano wire, on the other hand, will carry strains varying from 1 to 2 pounds to many hundreds of pounds, will stretch regularly under the tension, and will always resume its original length. Many hundreds of stretchings will not measurably increase the length of the wire. If the elastic limit is reached, however, the molecules will not resume quite their former positions. As before observed, the elastic limits for steel are very wide indeed. A plastic substance, such as lead, on the other hand, possesses almost no elasticity. Its reaction to molecular displacement appears in the form of heat generated among the molecules. A very little hammering will soon make a piece of lead too hot to touch, while the same work done upon a piece of iron of the same weight does not appreciably warm it, for the reaction comes mainly in the rebound of the hammer from the iron. Steel is more elastic than iron, and iron more than any other metal. The extreme elasticity of steel may be gathered from the results of experimental evidence, whereby it has been shown that a drawn steel wire 1 millimeter, 1/20th of an inch, in diameter returns completely to its original length so long as the stretching force is less than 32 kilograms, 70 pounds. Within this limit, therefore, steel is said to possess perfect elasticity. A drawn copper wire of the same diameter shows perfect elasticity only until the stretching force has reached 12 kilograms, about 26.5 pounds. Robert Hooke, a contemporary and friend of Newton, formulated about the end of the 17th century what is known as Hooke's law, which states, within the limits of perfect elasticity, plastic deformation of any sort, be they twists or bends or stretches, are directly proportional to the forces producing them. This means simply that a rubber ball, a steel ball, an ivory ball, or almost any sort of solid body will, if compressed, resume its former shape as soon as the pressure is removed, provided that the compression has not been too great. The greater the strain necessary to produce a small deformation, the greater is said to be the elasticity of the body. Gases alone possess perfect elasticity for all degrees of pressure. All gases under pressure tend to expand indefinitely upon the release of the pressure. By sufficient pressure and extreme cold, all gases may be so far reduced in volume that they become liquid. The liquefaction of gases was first successfully accomplished by Michael Faraday about 1823. Other experimenters followed, but no great advance in this direction was made until 1877, when Cailletet and Pictet, working independently, succeeded in liquefying oxygen. Their process consisted in compressing the gas into a small tube, cooling it, and then suddenly allowing it to expand by removal of the pressure. The principle is essentially the same as that in use today, and there exists no gas which has not been examined in the liquid state. Most gases, as such, are colorless. Oxygen gas has no color, but liquid oxygen is milky white. Hydrogen gas, as such, is colorless, but liquid hydrogen is steel blue. End of section 3. Section 4 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 2, The Properties of Matter, Part 2. As before observed, sufficient pressure will reduce most gases to the liquid state. It is a remarkable fact, however, that a temperature has been determined for every common gas above which no amount of pressure, however great, will succeed in making it liquid. This critical temperature varies for different gases. Liquid air cannot be produced at a temperature higher than 220 degrees Fahrenheit, below zero. Hydrogen must be cooled to a temperature of more than 400 degrees below zero before it can be liquefied. The terms frigid and icy are hopelessly inapplicable to these terrific degrees of cold, for ordinary ice, as is well known, is so warm that a vessel of liquid air placed upon a block of ice will boil violently, while the temperature of the liquid hydrogen is nearly as far below that of the liquid air as the latter is below the freezing point of water. It might be interesting to note, in passing, that hydrogen, which for a long time resisted all efforts at liquefaction, was finally produced by James Dewar in 1902, not merely as a liquid, but as a solid. This he accomplished by expanding liquid hydrogen into a space continually exhausted by an air pump, reaching thereby the incredibly low temperature of 430.6 degrees Fahrenheit below zero. The history of experimentation upon the weight and expansive force of gas teems with interesting incidents. The doctrine that nature abhors a vacuum was a part of the scientific gospel up to the time of that remarkable group of men who followed Copernicus, Galileo, and Gilbert. Galileo had proved that air has weight by weighing a glass globe, forcing more air into it and weighing it again. The increase of weight he rightly attributed to the added air. It did not occur to him, however, that the weight of air had anything to do with nature's horror of a vacuum. He was amazed when informed that a lift pump had been constructed with a tube about 40 feet long, and that no amount of pumping would cause the water to rise higher than about 33 feet. He observed that nature's horror of a vacuum was an instinct which she did not always display. Above the water was a vacuum, but the water refused to fill it. So, said he, nature's dislike of vacuum might be measured by the height of the column of water which it would support. Galileo's friend and pupil, Torricelli, musing over this suggestion, came to the conclusion that the weight of the water in the suction pipe was supported by the weight of air upon the cistern outside. Torricelli knew that mercury was about 13 times as heavy as water. He reasoned that the air ought to support a column of mercury 1/13 as high as the column of water in the suction pump. He had a glass tube made about 33 inches long, closed at one end and completely filled with mercury. Closing the open end of the tube with his finger, he inverted it in a dish of mercury. The mercury sank a little way in the tube and came to rest with its surface 30 inches above the free surface of the mercury in the vessel below. Torricelli had constructed the first barometer. The name of Pascal is indissolubly associated with the hydraulic press. He was interested, however, in Torricelli's novel experiment, and, having tried it, concluded that the vacuum is not impossible in nature, and she does not shun it with so great horror as many imagine. Pascal reasoned that if one were to ascend a mountain, the pressure of the air at the greater elevation should be less, because there would be less air overlaying the mountain top than there was overlaying an equal area of the plain. Accordingly, he wrote to his brother-in-law, who lived near the Puy de Dôme, an ancient volcano in the Auvergne, France, asking him to ascend the mountain with a Torricellian tube and observe whether the mercury column would not fall because of the diminished atmospheric pressure. The experiment was made, and it was found that the mercury column became 3 inches shorter during the ascent, but gradually resumed its previous length during the descent to the plain. Pascal also repeated Torricelli's experiment with wine instead of mercury, and he found, as he had inferred, that since wine is less dense than water, the atmosphere balanced a column of it, which was longer than the water column, for of course it would take a longer column of the lighter fluid to make the same weight. The hypothesis of Torricelli and Pascal as to the pressure of the atmosphere was thus placed upon a firm experimental basis, and was now competent to explain the phenomena of pumps, but it required the evidence of many more experiments to secure its general acceptance. The most remarkable man of this period, however, in view of the multitude and the ingenuity of his experiments, was Otto von Guericke, who later became mayor of the city of Magdeburg. The Magdeburg hemispheres have become a familiar word owing to his famous experiment made in 1654 at Regensburg before the Reichstag and the German Emperor Ferdinand III. 2 hollow hemispheres of steel, about 1.2 feet in diameter, were cast for his remarkable experiment. They were fitted at either end with heavy iron rings and provided with a tube and stopcock. The edges were made broad and smoothed and polished to a perfect plane so that they might fit exactly together. Then the air was pumped out of the interior, the stopcock turned off, and 12 horses, 6 at each end, were hitched to the rings of the hemispheres. Their combined efforts failed to overcome the pressure on the outside of the spheres. Another team of horses was attached, and yet another, and the spheres were finally pulled apart. A simple calculation will show that this result was inevitable, the average horse, it is estimated, being able to exert a pull equal to about 600 or 650 pounds horizontally. According to the known formula for the surface of a sphere of 12 feet diameter, these hemispheres would have about 652 square inches area. Reckoning the atmospheric pressure upon the outside of the 2 hemispheres at 15 pounds to the square inch, and assuming that the internal pressure has been reduced to a negligible quantity, it is apparent that the pressure to be overcome would equal, roughly, 9,780 pounds. According to von Guericke's calculations, a force of 2,686 pounds would overcome the atmospheric pressure upon the exterior of the spheres. Here must be some error. There is extant a quaint old engraving showing the horses endeavoring to separate the exhausted hemispheres. On the occasion of this experiment, von Guericke asserted that if you were to blow your breath into a large exhausted receiver, you would at that moment breathe your last. The truth of this being doubted, he illustrated the power of suction by a new experiment. A cylinder of a large pump had a rope attached to its piston, which led over a pulley and was divided into branches on which 20 or 30 men could pull. As soon as the cylinder was connected with an exhausted receiver, the piston was suddenly pushed down by the atmospheric pressure, and the men at the ropes were thrown forward. The air pump used by the distinguished mayor of Magdeburg was his own invention. The upper bulb was of glass. A glance will show that the instrument was but a clumsy affair compared with those in use today. A better pump was made by Boyle and Hooke in England some 6 years later. It was not long after these remarkable experiments of von Guericke that Robert Boyle published his New Experiments Touching the Spring of the Air, and stated the law which has since borne his name. Under like conditions of temperature and pressure, the volume of a gas varies inversely as the pressure upon it. We took then a long glass tube, he writes, which by a dexterous hand and the help of a lamp was in such a manner crooked at the bottom that the part turned up was almost parallel to the rest of the tube, and, the orifice of this shorter leg being hermeneutically sealed, the length of it was divided into inches, each of which was divided into 8 parts, by a straight list of paper, which, containing these divisions, was carefully pasted all along it. A similar strip of paper was pasted on the longer leg. Then, as much quicksilver as served to fill the arc or bended part of the siphon was poured in so as to be at the same height in both legs. This done, we began pouring quicksilver into the longer leg, till the air in the shorter leg was by condensation reduced to take up but half the space it possessed. We cast our eyes upon the longer leg of the glass, and we observed, not without delight and satisfaction, that the quicksilver in that longer part of the tube was 29 inches higher than the other. Experimentation in measuring the weight of the air was naturally followed by efforts at more exact estimations of temperature. The air thermometer of Galileo was an exquisitely sensitive instrument, but having an exposed liquid surface, was subject to barometric influences as well as those of heat and cold. Fahrenheit, toward the end of this century, devised a thermometer which bears his name. He selected his zero at the lowest temperature which he knew how to obtain, and took the highest fixed point at the temperature of the human body. He divided the space into 24 equal parts, and then, finding these degrees too large, subdivided each into 4 parts, thus making the temperature of the body 96 degrees. On this basis of division, the freezing point of water happened to come at 32 degrees, and the boiling point of water at 212 degrees. And there they stay to this day, despite the fact that all modern physicists measure temperature on the excellent centigrade scale of Celsius, whereon the freezing point of water is 0 and the boiling point 100 degrees. Nearly a century after the invention of Fahrenheit's thermometer and 50 years after that of the Swedish astronomer Celsius, need was found for a third type of thermometer. The experiments of Charles Dalton, Guy Lussac, and others had determined the fact that for every degree centigrade of increase in temperature above 0, the volume of a gas increased by 1/273rd of itself. Similarly, a decrease of 1 degree below 0 meant a decrease of 1/273rd in volume of the gas. A decrease of 2 degrees meant a reduction in volume of 2/273rds. Hence, a fall of 273 degrees would mean a reduction of 273/273, or, in other words, the volume of the gas would be reduced to 0. This was absurd, for the law of the indestructibility of matter would not allow that something could become nothing. The explanation, however, soon was found in the fact that all gases become liquid before reaching this point, and it is a matter of common knowledge that liquids are practically non-compressible. The temperature of 273 degrees centigrade was then taken as the 0 of the absolute scale, because it was believed, and there is no evidence yet to disprove it, that at that temperature the molecular motions of all bodies would entirely cease, the molecules would be perfectly at rest. With this thermometer in mind, the statement of the law of gases, called Charles's law, or Gay-Lussac's law, is simple. It was, the volume of a gas varies directly as the absolute temperature. Brief mention herein has been made of the remarkable experiments of William Crookes upon the so-called cathode rays in the highly exhausted tubes which have since borne his name. In the course of his investigations upon the properties of the newly discovered element, thallium, he attempted to carry out the necessary delicate weighings in a vacuum in order to avoid the effect of the buoyancy of the air. Irregularities in the weighings, which he was quite unable to explain, led him to the invention of his famous radiometer, an instrument now common enough in the windows of optician stores. It consists of a delicate paddle wheel with 4 metallic vanes, polished on one side and blackened on the other, mounted so as to revolve in a partially exhausted tube. Light falling upon the dark surfaces is absorbed, and the temperature of the residual gas next to these surfaces is therefore raised in accordance with the well-known fact that black is a warmer color than white. Higher temperature means greater molecular activity, as will appear in the chapter on heat. Hence, the vanes are pushed backward to the region of the comparative quiet on the polished side. When the light is withdrawn, the revolution ceases, and the brighter the light, the faster the revolution. At first, Crookes believed the rotation of the vanes to be due to ether waves, but by exhausting the bulb to an extremely high vacuum, he found the wheels did not revolve. He therefore fell back upon the modern kinetic theory of gases, attributing the motion to the bombardment of the vanes by the molecules of gas left in the tube. End of section 4. Section 5 of The Science History of the Universe, Volume 3. This is the LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 2, The Properties of Matter, Part 3. The examination of the properties of gases began naturally with the study of air. Similarly, the inquiries of the human mind into the characteristics of liquids began with an investigation of the properties of water. The story of Archimedes and the crown problem is probably the earliest historical record of the study of hydrostatics, though Pliny makes mention of a Phoenician who devised a highly ingenious scheme for transporting along the Nile 2 great columns of an Egyptian temple. The columns were rolled in huge cylindrical boxes drawn by oxen to the bank of the Nile. There the bank was dug away from under them until they rested on their ends, when 2 large scows full of sand were floated underneath them. The sand was then thrown out, the boats rose, and the pillars took the place of the sand. No systematic study of displacement and pressure in liquids, however, was made before the time of Blaise Pascal. In 1653 there appeared his Traité de l'équilibre des liqueurs, in which he enunciated the law known by his name, to wit, pressure applied anywhere to a body of confined liquid is transmitted by the liquid so as to act with undiminished force on every part of the containing vessel. Whereby, he said, it follows that a vessel full of water is a new principle of mechanics and a new machine for multiplying forces, to any degree we choose. The hydraulic press is the direct outcome of Pascal's principle of transmitted pressure. The mechanical advantage of the machine depends simply upon the relative size of the surfaces at which the force is applied and the power produced. If, for instance, the piston of the pump has an area of 10 square inches and the press itself has contact with the water over a surface of 1,000 square inches, the result will evidently be a power of 100 times as great as the force. The pressure will move, however, only 1/100th as far as the pump piston, for force is indestructible. The particles of liquid being constantly in motion, it follows that, although every molecule attracts every other molecule in a vessel of water, yet some of the molecules constantly will be acquiring as a result of collision or temperature a speed which will carry them beyond the attraction of other molecules. This is what is meant by evaporation. The larger the exposed surface of the liquid, the greater the possible number of escaping molecules. This explains why water evaporates so much faster when boiling than when cool, for the free surface of the liquid is enormously increased by the presence of the bubbles. When a vessel of water is heated, bubbles of gas are first seen to collect around the sides and on the bottom of the vessel. These are bubbles of dissolved air, of which all water contains a certain proportion. As the temperature rises, the particles of air, owing to their increased molecular velocities, are forced out of solution, combining to form bubbles. When all of the air has been driven out, the water at the bottom of the vessel, owing to excessive heating, is vaporized bodily, and the phenomenon of boiling appears. The air dissolved in water gets into it in exactly the same way that water gets into the air, viz. By evaporation. Similarly, liquids dissolve in each other, as chlorine or alcohol in water. Pressure upon the surface of a liquid makes boiling more difficult. The movement of molecules in the liquid and the gas, air, above it, will readily explain this fact, for as Robert Boyle showed in the case of gases, that under pressure they have a smaller volume. Since the same number of molecules must still be there present, the molecules of gas above the liquid will be closer together and will leave less room for the molecules of the liquid to jump away from the surface. Following this reasoning, it is to be expected that if a vacuum exists above the free surface of a liquid, the latter will evaporate more rapidly. Such is indeed the fact, and a very pretty demonstration of it may be made thus. If a watch glass with a little ether in it be placed upon a drop of water under the receiver of an air pump, and the latter exhausted of air, it will be found at the end of a couple of minutes that the watch glass is frozen fast to the floor of the receiver. The ether evaporates so rapidly under these conditions that the temperature of the water is reduced to freezing. Otto von Guericke remarked that when he had connected a large exhausted receiver to the air space above a cask of wine, there followed a loud boiling noise, which continued for some time. He did not know how to explain the sound, but today, with the aid of experimenters of nearly 3 centuries, it would be accounted for by saying that the exhaustion of the air which rushed into the receiver caused such a rapid evaporation of the wine in the cask as to produce the phenomena of boiling. Exactly similar results may be produced by half filling a thin bottle or flask with boiling water. If the flask be now tightly corked and inverted, the application of any cool substance, such as a wet cloth, or the pouring of cold water over the bottom, will cause a contraction of the vapor-laden air within. This contraction, by relieving the pressure upon the surface of the water, will cause the latter to boil again. The operation may be repeated many times without reheating. The question naturally suggests itself in this connection. Why is evaporation a cooling process? An answer may readily be found in that extremely serviceable kinetic theory of gases. If the molecules of a gas are traveling, as has been pointed out, in open parabolic paths, these curving orbits are likely to intersect more frequently when the molecules are crowded and jostled together than when left comparatively free and untrammeled. A man walking along a country road feels far less conflict with the surrounding objects of nature than with the busy throng which hustle him and the cares that crowd upon him in the swarming city streets. His mental state is more placid, cooler. So it is with those entities called molecules, and the greater the expansion, the more marked will be the fall in temperature. The question may even be asked as to why a gas expands into a vacuum. For the present, an answer must be found in the equilibrium of forces and the fact that particles of matter, like the charged corpuscles of an electric current or the drops of water in a flowing stream, follow the path of least resistance and move in the direction determined by the sum of the forces acting upon them. On this basis may also be explained the familiar phenomena of capillary and osmose or diffusion in liquids. The fact that a lump of sugar, if allowed to stand for a while, will sweeten a whole glass of water without stirring. Evaporation is but an instance of the adjustment of forces to an equilibrium. When the air above a dish of water is confined by a cover, evaporation will proceed only until the vapor is saturated with the particles of water which have jumped out of the dish. When the point of saturation is reached, there will be as many molecules leaping back to enter the liquid as those which free themselves from its surface. Evaporation, therefore, will cease. In the same way, solids whose particles are evaporating from the surface may saturate the air around. If the air is confined, evaporation will cease at saturation. Camphor, which is carefully protected from air, will act for many months or even years as a deterrent to moths. But if left exposed, the rapidity of its evaporation is shown by the fact that a piece of camphor brought into a room may be detected from any part of the room in a few minutes. The exquisite odor of a bunch of roses will quickly perfume a large room, and the perfume of flowers consists of the particles of matter being thrown off by evaporation. Not greatly unlike the phenomena of crystallization in the fixation of its molecular properties is magnetism, one of the oldest observed physical phenomena. Pliny says the word magnet is derived from the name of the Greek shepherd Magnes, who on the top of Mount Ida observed the attraction of a large stone for his iron crook. It was also known to the ancients that artificial magnets may be made by striking pieces of steel with natural magnets, but it was not until about the 12th century that the discovery was made that a suspended magnet will assume a north and south position. The compass, said to have been introduced into Europe from China, appeared first about 1190. The incalculable value to the world of this discovery is patent. It meant scientific navigation, exploration, and the discovery of the New World. With Galileo in Italy, the originator of modern physics, may well be placed William Gilbert, the father of the magnetic philosophy. Gilbert was appointed by Queen Elizabeth her physician in ordinary, and she settled upon him an annual pension for the purpose of aiding him in the prosecution of his philosophical studies. His first investigations were in chemistry, but later, for 18 years or more, he experimented on electricity and magnetism. In 1600, he published his famous treatise, De Magnete, in which he showed, as a result of careful experimentation, that the compass points to the north, not because of some mysterious influence of the stars, but because the earth itself is a great magnet. In reading over the 6 books of this great work, one cannot fail to be struck by the variety of the author's accomplishments. He writes in Latin and intersperses his pages with frequent Greek quotations. He is familiar with poets, historians, philosophers, and discusses with clearness and fullness all the chemical and physical knowledge of previous ages. The work is truly monumental. It also contains Gilbert's own numerous valuable and costly contributions to magnetic science. First among these is his grand generalization, the new and till now unheard of view, that the earth is a great magnet, and he is not afraid to say that this novel view will stand as firm as aught that ever was produced in philosophy, backed by ingenious argumentation or buttressed by mathematical demonstration. Gilbert's contempt for the methods of the schoolmen crops out everywhere in his book. Why should I, he writes boldly, submit this noble and this new and inadmissible philosophy to the judgment of men who have taken oath to follow the opinions of others, to the most senseless corrupters of the arts, to lettered clowns, grammatists, sophists, spouters, and the wrong-headed rabble, to be denounced, torn to tatters, and heaped with contumely? To you alone, true philosophers, ingenious minds, who not only in books but in things themselves look for knowledge, have I dedicated these foundations of magnetic science, a new style of philosophizing. Gilbert did not explain, nor has any satisfactory explanation yet been offered as to why iron and steel are the only substances which exhibit marked magnetic properties. Nickel and cobalt are appreciably attracted by a strong magnet, but the other metals, copper, zinc, tin, lead, etc., show complete indifference to magnetic influence, while bismuth and antimony are actually repelled by it. In this unique restriction of its application to one or two substances, magnetism as a force stands alone. It is generally held to be due to a molecular adjustment. The fact that magnetic iron heated red hot and beaten loses its magnetism, that a magnet hung north and south and beaten likewise loses its magnetism, make it apparent that magnetism is due to the arrangement of the molecules of the magnetized body. The expansive tendency of the molecules of a gas under ordinary conditions of temperature and pressure is quite different from the behavior under like conditions of the molecules of a liquid or a solid. There is every reason to suppose that the molecules of an unconfined gas would expand indefinitely into space. In accordance with current belief, the molecules of every substance are in motion. In the solid state, writes a prominent American physicist of today, it is probable that the molecules oscillate with great rapidity about certain fixed points, always being held by the attractions of their neighbors, i.e. by the cohesive forces, in practically the same position with reference to other molecules in the body. In rare instances, however, as the facts of diffusion show, a molecule breaks away from its restraints. In liquids, on the other hand, while the molecules are in general as close together as in solids, they slip about with perfect ease over one another and thus have no fixed positions. This assumption is necessitated by the fact that liquids adjust themselves readily to the shape of the containing vessel. In gases, the molecules are comparatively far apart, as is evident from the fact that a cubic centimeter of water occupies about 1,600 cc's when it is transformed into steam, and furthermore, they exert practically no cohesive force upon one another, as is shown by the indefinite expansibility of gases. A highly illuminating discussion of the actual motions of molecules in these three fundamental states of matter has recently been given by J.W. Richards, president of the American Electrochemical Society, in an article entitled Kinetic Molecular Energy. Dr. Richards writes, "The conditions of molecular motion is chiefly determined by velocity. According to the velocity of the molecules, we have solids, liquids, and gases. Within the lowest range of molecular velocity, the movement of the molecules is oscillatory. We have a fixed relative position. The body has a size or shape. It is a solid. Within the next higher range of molecular velocity, the velocity is able to carry the molecules just beyond the reach of opposing forces. The molecules move in closed elliptic orbits, like the planets round the sun. The body loses its form and shape but retains its volume. It is a liquid. When the molecular velocity is raised still farther, the molecules move in open parabolic paths. The body not only has no shape or form, but actually tends to increase its volume. It is a gas. If attraction is exerted between the molecules of a substance, it must be conveyed by some medium other than matter. This conclusion is involved in the hypothesis of the granular nature of matter, for force acting at a vacuous distance is unthinkable, or at best incomprehensible. The cohesion of the molecules of a substance thus resembles gravity, which reaches across the enormous interplanetary spaces to grasp the masses of the planets and hold them in their courses round the sun. Like gravity also, the cohesive force which renders substances elastic does not seem to consist of material vibration or ether disturbances. Cohesion acts through infinitesimal spaces upon bodies infinitesimally small. Gravity spans distances immeasurable to guide a myriad of suns and systems. Yet both these forces are conveyed through a medium at once infinitely rigid, since it is non-compressible, and infinitely fine, since it is frictionless. The distinguished author of the electromagnetic theory of light, speaking of the characteristics of the ether, writes, "The vast interplanetary and interstellar regions will no longer be regarded as waste places in the universe, which the Creator has not seen fit to fill with the symbols of the manifold order of His kingdom. We shall find them to be already full of this wonderful medium, so full that no human power can remove it from the smallest portion of space or produce the slightest flaw in its infinite continuity. It extends unbroken from star to star, and when a molecule of hydrogen vibrates in the dog star, the medium receives the impulses of these vibrations, and after carrying them in its immense bosom for several years, delivers them in due course, regular order and full tale, to the spectroscope." End of chapter 2.
Section 6 of The Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 3, Heat. Part 1. It has been said that the history of man begins with the discovery of fire. How many conveniences of modern life are dependent, in the last analysis, upon the use of fire? It would be hopeless to attempt to enumerate. The survival of the human race, with its primitive, undeveloped physique, helpless for defense or attack except by virtue of superior cunning, would never have been possible without the aid of fire. It is, indeed, a well-known fact that life in any form is directly dependent for its development upon conditions of temperature. The myriad forms of physical life that are hourly born upon the surface of the globe owe their existence to the heat radiated from a gaseous ball some 93 million miles away. All the heat in the world, excepting the negligible quantity reflected from the moon or transmitted from the stars, must be traced originally either to falling meteorites or to the sun. The warmth of the air, the rocks, and the water is derived from these sources. Even the heat of a coal or wood fire is but an expression of solar energy, for it was the sun's heat which, through the growth of vegetable tissue yesterday, or 1,000,000 years ago, transformed the incombustible soil into a form apt for the burning. The heat received by the earth from meteors would be nearly the same in amount as that which it receives from the sun by radiation, but for the probable circumstance that these meteors, reaching the earth's atmosphere at an exceedingly low temperature, radiate most of the heat engendered in their approach into outer space. For practical purposes, then, the sun may be considered as the original source of all terrestrial heat. No material body, it is true, is quite devoid of heat, for as long as its molecules are in vibration, matter must radiate into the space surrounding this vibratory energy. Heat as a physical phenomenon, then, is the vibration energy of molecules of matter, solid, liquid, or gaseous. Here must be noticed the difference between radiant heat, so called, and molecular heat. In the form of radiant heat, energy is transmitted by the sun to the earth. It is converted from radiant heat into molecular vibration upon contact with the matter of the earth, and the material bodies, so incited, afford the phenomenon commonly known as heat. Anything like an exact study of heat was never possible before the disassociation of the ideas of the vibratory phenomenon of heat and the sensation of it. By the use of his sense of touch mainly, man has learned to decide in a general way whether a body is hot or cold, and whether it is gaining heat or losing it. Conclusions based on this sense of temperature, however, are likely to be very inexact, or even wholly false. The sensation of heat may often be mistaken for that of cold, and vice versa. If one hand is put into ice-cold water, and the other into water as hot as it can endure, and after a minute or two both hands are thrust into water at blood heat, 98 degrees Fahrenheit, this same water will feel cold to one hand and warm to the other. Evidently, the temperature sense is a relative matter. Heat as a sensation must be relegated to the domain of medicine or psychology. Heat as a form of vibration, however, is a legitimate object of physical investigation. Previous to the 19th century, physicists generally considered heat as an invisible, weightless fluid, which by passing into or out of a body caused it to become hot or cold. This view accorded readily enough with the facts observed in the heating of a body held in a flame or near another hot body. It did not account for the heat produced by friction. In 1798, Benjamin Thompson, Count Rumford, an American by birth, brought forward the molecular theory of heat, according to which the increase in the temperature of a body means simply an increase in the average velocity of its molecules. This theory, tried out and carefully tested by the great English physicist James Prescott Joule in an exhaustive series of experiments, has proved thus far the best working hypothesis of the nature of heat. The earliest traces of the theory that heat is matter, writes Florian Cajori, are found in ancient Greece among Democritus and Epicurus. In modern times, it was advocated by Pierre Gassendi and George Ernst Stahl, author of that erroneous theory of combustion, according to which a burning body gave off a substance called phlogiston. One such agent paved the way for the other. In 1738, the French Academy of Sciences offered a prize question on the nature of heat. The winners of the prize favored the materialistic theory. At first, the only properties postulated for this material agent, called heat, were that it was highly elastic and that its particles repelled each other. By this repulsion, the fact that hot bodies give off heat could be explained. Later, it was assumed that the heat particles attracted ordinary matter, and that this heat was distributed among bodies in quantities proportional to their mutual attractions, or their capacities for heat. By the close of the 18th century, this theory met with almost universal acceptance. Marat, afterward famous as a leader in the French Revolution, gave in 1780 an exposition of this theory by starting from Newton's corpuscular theory of light. Professor Clerk Maxwell, in his Theory of Heat, says, "We must therefore admit that at every part of the surface of a hot body there is radiation of heat, and therefore a state of motion on the superficial parts of the body. Now, motion is certainly invisible to us by any direct mode of observation, and therefore the mere fact of a body appearing to be at rest cannot be taken as a demonstration that its parts may be in a state of motion. Hence, part at least of the energy of a hot body must be energy arriving from the motion of its parts. Every hot body is, therefore, in motion, the movements of the parts being too small to be observed separately." Tyndall defined heat as a mode of motion. It might more accurately be defined as a mode of motion of the particles of a mass. The greater the heat, the greater will be the motion of the particles. In accordance with the molecular theory discussed in the chapter on the properties of matter, any increase in temperature means simply this, and nothing more: an increased velocity of the molecules of the heated substance. If, then, the temperature of a body be lowered until the point of absolute zero is attained, there will then be no motion of its molecules. Nothing but mass would remain, absolutely motionless, and in a state of perfect tranquility and rest. To speculate as to the probable condition of matter when the point of absolute zero has been passed, and the molecular motions have become, so to speak, negative, might be interesting, but not profitable. As yet, the temperature of absolute zero has never been attained, and all matter as known today is possessed of some molecular motion, some heat. The late Lord Kelvin has surmised that the ether may be constituted of the dissipated dust of atoms which have lost all vibratory motion of their own. This is admittedly a guess, and does not affect the generally accepted belief that ponderable matter is ever in vibration. The measurement of heat may be considered in any one of three ways. It is possible first to measure the degree of heat in a body, as did Galileo with his air thermometer as early as 1592. Measurements of this kind, made with solids, liquids, and gases, have resulted in the establishment of extremely valuable physical data, more especially in the field of meteorology. Secondly, the actual amount of heat in a body may be measured. It is evident that a red-hot needle possesses a smaller amount of heat than a stove which is only moderately hot. The determination of the amount of heat possessed by a body constitutes the science of calorimetry. The calorie, or heat unit, is defined as the amount of heat necessary to raise 1 cubic centimeter of water through 1 degree centigrade. Joule reasoned that if the heat of friction were merely mechanical energy which had been transferred to the molecules of a heated body, then the same number of calories must always be produced by the expenditure of a given amount of mechanical energy. His investigations in calorimetry, whereby he determined the mechanical power corresponding to a given amount of heat, first proved experimentally the identity of various forms of energy. In a series of experiments lasting over nearly 30 years, he caused mechanical energy to disappear in as many ways as possible, and measuring the amount of heat developed, found it to be for a given amount of energy in each case the same. Thus was established the principle of the mechanical equivalent of heat. The English physicist found that the equivalent of the calorie in work was equal to 426.4 kilogram meters, parenthetically 3,081 foot-pounds. That is to say, the amount of heat necessary to raise 1 cubic centimeter of water 1 degree centigrade would, if all converted into work, be sufficient to raise 3,081 pounds through 1 foot of height, or what is the same thing, to raise 1 pound through 3,081 feet. The mechanical equivalent of heat is such an important constant in nature that several physicists since Joule have thought it desirable to redetermine it. One of the most accurate determinations was made in 1879 by Henry A. Rowland of Baltimore. He obtained 427 gram meters as the mechanical equivalent of the calorie. A third method of measuring the heat of a body is a relative one. Specific heat is a term used in comparing the relative amounts of heat necessary to increase equally the temperature of equal weights of different substances. For example, glass and water. It has been found that more heat is required to raise the temperature of a pound of water, say 10 degrees, than to increase to the same extent the temperature of an equal weight of almost any other substance. Therefore, water is taken as a standard of specific heat, and when the heat necessary to raise the temperature of glass 10 degrees is found to be 5 times as great as that necessary to raise the temperature of an equal amount of water 10 degrees, the specific heat of glass is determined at 1/5, or 0.2. The value to the physicist and chemist of determining specific heats of substances is great, for a fixed relation has been found to exist between the specific heats of solids and their atomic weights. For this significant discovery, science is indebted to the researches of Berzelius, Raynaud, Dulong, and Petit. Matter is variously affected by heat. In general, it increases the volume of a body, but just as magnetism has sometimes the contrary effect, as for instance its contractile influence upon nickel, so heat has sometimes the effect of reducing a body. Water, for example, is denser at 40 degrees Fahrenheit than at freezing, which is proven by the fact that ice floats, having about 1/10 of its volume out of water. Were it denser than water, this could not be. Again, type metal contains a small proportion of antimony, since antimony expands on solidifying, making the perfect sharp outline indispensable to good type. With the exceptions noted, however, the law is general that bodies contract with cold and expand with heat. Railway rails are always laid with a slight space between them to allow for the expansion in the hot days of summer. Iron bridges frequently have a roller at one end to provide for the difference of length. The steel suspension cables of a bridge a mile long will vary in length nearly 4 feet between summer heat and winter cold. If the heat applied to a substance is strong and continuous, the result is a change of state. Solid ice becomes water, water becomes a vapor. A great deal of energy is absorbed in this transformation of state. It takes nearly as much heat to change a pound of ice into a pound of ice water as to heat the same water to boiling. It takes more than 5 times as much heat to change the water into steam as to raise its temperature from freezing to boiling. Conversely, a great amount of energy is liberated by the condensation of steam, a fact well illustrated in the immense power of the steam engine. And no small amount of heat is set free when water freezes. The country in the neighborhood of large lakes is thus appreciably warmed by the congelation of the water. For exactly the same reason, the farmer often places tubs of water in his cellar, that the freezing of the water may sufficiently warm the air to keep his vegetables from freezing. End of section 6. Section 7 of The Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 3, Heat, Part 2. More remarkable than the effect of the freezing of water upon the surrounding air is that of evaporation. As the freezing of water in winter warms the air, so the evaporation of water in the open seasons of the year will cool it. The amount of evaporated water which can exist in the air depends upon the temperature. If the air has absorbed all the water vapor which it is capable of holding, it is evident that a fall in temperature will succeed in condensing a part of the suspended water vapor, which then falls as rain or settles as mist. If the air is not completely saturated, it is evident that considerable cooling may take place before the dew point is reached and condensation of water begins. In the hot days of the summer months, the air is capable of taking up and holding in suspension a large amount of moisture. On such days, the oppressiveness of the heat is greatly augmented by the muggy condition of the atmosphere. The excessive moisture of the human body cannot escape into the air, for the latter is already surcharged with moisture, or nearly so. The grateful effect of a breeze is thus made clear, for the excess of moisture which evaporates from the body has no opportunity to saturate the air immediately around before a fresh supply of air appears to take up the exhalation from the skin. It was formerly held by scientific inquirers that the dew fell from the upper regions of the atmosphere. That idea has been quite swept away within recent times, and it is now known that the formation of dew is due to the condensation of water vapor in the air close to the ground. A heavy dew is said to be the forerunner of fine weather. It actually indicates an unusual fall in temperature from the heat of the day, nothing more. The formation of condensed particles of water vapor in the upper regions of the atmosphere is generally conceded to be due to the impalpable dust particles which float everywhere in the terrestrial atmosphere, rising to considerable heights. As water vanishes so strangely into the thin vapors of the air, so solid bodies have been observed by everyone to disappear and dissolve in liquids. There are probably few persons, if any, who have not noticed that sugar dissolves more readily in hot water than in cold, while salt is about equally soluble in both. In general, the solutions of solids in water or any other solvent are made easier by the application of heat. So also with solutions of liquids, for the viscosity of most liquids is reduced by the application of heat. They become less dense and therefore mix more readily with the molecules of the liquid in which they are dissolved. Solution is such a familiar everyday phenomenon that the complete disappearance of solid material in a liquid is taken as a matter of course. Yet it is truly a wonderful thing that a lump of sugar or a teaspoon of salt dissolved in a glass of water will not raise the level of the water, and so soon as solution is complete, will leave absolutely no visible trace of its presence. As the temperature is raised, more of the solid may be made to disappear. Even boiling water, however, will take up but a limited quantity of a solute, and on cooling, this may readily be seen by dropping in a crystal of the dissolved material, or otherwise disturbing the mixture, causing it to exhibit the beautiful and fascinating phenomenon of crystallization. A strange contrast to this condition of things is found in the fact of the solution of gases in liquids. Here the effect of temperature is quite the reverse of what has just been observed. The cooler the liquid, the greater the quantity of gas which may be dissolved in it. The quantity of gas which may be dissolved by a single pint of water is amazing, in some instances almost incredible. Hydrogen chloride, for example, is soluble to the extent of over 300 pints in a single liter of water, and the same quantity of water will dissolve without artificial pressure 1,148 pints of ammonia gas. The effect of heat on a liquid, or indeed on any body, being recognized as an increase of its molecular velocities, the question arises as to how this increase of velocity is transferred from one part of matter to another. The most direct way for this to take place is by the transference of energy from one molecule to the next. In general, this is accomplished most readily by the molecules of a solid, especially solids of exceptional density, such as metals. For example, a short copper or iron wire held for a moment in a hot flame soon becomes too hot at the other end to hold. A silver wire will conduct the heat of the flame to the hand even more quickly. A stone feels colder to the hand than a piece of wood at exactly the same temperature, for the obvious reason that the stone, being a better conductor, carries off the heat of the body more rapidly. The tongue will freeze fast in winter to the blade of an axe, a fact well known in cold countries, where the bit of a horse's bridle cannot be put directly in his mouth if it has been out in the frosty air. The same axe blade lying in the summer sun will feel hotter than any other part of the axe. Liquids, however, are poor conductors, as has been shown by the fact that burning alcohol on the surface of water will register no perceptible heat in an instrument so sensitive as the air thermometer, whose bulb is placed but half an inch below the surface of the water. Gases are almost non-conducting. Dry air, writes a physicist of today, is a practical vacuum as regards the rays of heat. Liquids and gases, however, may carry considerable heat by the motions of comparatively large masses of themselves in a heated condition. This transference of heat by the movement of masses of a liquid or gas is termed convection. The term thus describes the manner in which temperature is adjusted by winds in the atmosphere and currents in bodies of water. Yet another method of the conveyance of heat is that by which most heat in the universe is carried, vis-à-vis radiation. The heat which is received from an open fire is not carried by conduction or convection, not by convection, for the movement of masses of air is all toward the fire, not away from it. not by conduction, for gases have been shown to be very poor conductors. The only other possible explanation of the passage of the heat rays must then be found in a non-material form of energy. To this form of heat transference, the term radiation has been applied. Radiation thus explains the sensation of heat felt from a burning house, even when the house is at a considerable distance, and the wind is blowing toward the fire. The method by which the heat of the sun is conveyed to the earth will likewise readily be seen to be the method of radiation. There could evidently be no mass movements, nor yet molecular movements, where is neither mass nor molecule. This radiant property must then be a function of the ether, not of matter in the mass. According to recent scholars, radiant heat must now be classed with light under the head of electricity. Three forms of heat transference, conduction, convection, radiation, are all to be seen in the consideration of the common steam or water radiator. Convection brings masses of hot water or steam from the furnace to the radiator. Conduction transfers the heat to the outside of the radiator. Radiation carries the heat to every part of the room to be heated. The application of heat to mechanical purposes has been astonishingly slow of development. From the time of the invention of Heron's eolipile, there elapsed 1,000 years before the idea of heat as a source of motive power was turned to practical account. Steam fountains were designed in the 17th century, but they were merely modifications of the eolipile and applied for ornamental purposes only. The first successful attempt to combine the principles and forms of mechanism then known into an economical and convenient machine was made by Thomas Newcomen, a blacksmith of Dartmouth, England. Assisted by John Galley, Newcomen constructed an engine, an atmospheric steam engine. In 1711, such a machine was set up at Wolverhampton for the raising of water. Steam passing from the boiler into the cylinder held the piston up against the external atmospheric pressure until the passage between the cylinder and boiler was closed by a cock. Then the steam in the cylinder was condensed by a jet of water. A partial vacuum was formed, and the air above pressed the piston down. This piston was suspended from one end of an overhead beam, the other end carrying the pump rod. The flywheel was introduced in 1736 by Jonathan Hulls. The next great improvements were introduced by James Watt in Scotland. Becoming interested in the steam engine and its history, he began to experiment in a scientific manner. He took up the study of chemistry under the guidance of Joseph Black, the originator of the doctrine of latent heat. Observing the great loss of heat in the Newcomen engine due to the cooling of the cylinder by the jet of water at every stroke, he began to ponder on the possibility of keeping the cylinder always as hot as the steam that entered it. He himself tells how there flashed through his mind the happy thought of how this could be done. "I had gone to take a walk," he says, "on a fine Sabbath afternoon. I had entered the green by the gate at the foot of Charlotte Street, and had passed the old washing-house. I was thinking upon the engine at the time, and had gone as far as the herd's house, when the idea came into my mind that, as steam was an elastic body, it would rush into a vacuum, and if a communication were made between the cylinder and an exhausted vessel, it would rush into it, and might be there condensed without cooling the cylinder." This improvement it is, by right of which James Watt may justly be called the inventor of the steam engine. The steam engine, as such, has practically reached its maximum of efficiency. Only about 22% of the heat energy furnished by the coal consumed is actually converted into work, even in the best triple expansion engines. The efficiency of the locomotive is even lower, being about 17%. The steam turbine, the latest development of the steam engine, is in principle very much like the common windmill, the steam being driven at an angle against a multitude of little blades set in a revolving cylinder of steel, the shaft. In large sea-going vessels, this engine is rapidly replacing the old-fashioned reciprocating machine. For its efficiency is higher, it occupies less than 1/10 the floor space, and it runs without jarring the ship. The highest speeds ever attained by vessels at sea, namely about 40 miles per hour, has been made with the aid of steam turbines. The construction of a turbine is an exceedingly difficult operation, for each of the little blades must be set singly into the shaft at exactly the right angle. Skilled workmanship and much time are required in this operation, and in view of the mechanical difficulties of constructing a turbine, it does not seem so remarkable that this engine, of which the extremely simple principle was familiar to Hero of Alexandria 120 BC, should have waited over 2,000 years to see perfection. The efficiency of the steam engine is measured by the fall in temperature which the steam undergoes in passing from the boiler through the cylinder, thus driving the pistons, to the condenser. It is evident that as this heat is made to disappear, work must be produced. The greater the fall in temperature, then, the higher the efficiency of the engine. Unfortunately, the steam engine is limited in this regard, for the highest temperature that can safely be maintained in the boiler is about 200 centigrade, the steam being then under a pressure of 15 atmospheres, or 225 pounds upon every square inch of surface. The lowest practicable limit of temperature in the condenser is about 30. Hence the loss of heat and the resulting efficiency will be measured by a fall of 170 degrees, 200 minus 30. A perfect steam engine should render about 36% of its heat energy into work, but owing to friction and other causes, no steam engine has ever been made which approaches this degree of efficiency. The gas engine has a considerably larger range of temperature fall possible in its mechanism. The explosion of the gases takes place at a very high temperature. Engineers predict that the gas cylinder engine and turbine engine will before long supplant the corresponding types of steam-driven machines. In conclusion, then, heat must not be considered as a weightless fluid, for the interchange of heat and mechanical energy is not consistent with this belief, nor is heat latent any more than the lifting power of a steam crane is latent. All the evidence of today points to the conclusion that heat is only one of the many forms of vibration. The effect of heat upon any material body is an increased rate of vibration of its molecules. The heat that reaches the earth from the sun, however, traverses the intervening space without heating it, as the intense cold of the upper regions of the atmosphere clearly indicates. It is therefore a property of the ether that it transmits vibrations without being itself affected by them. In matter, on the other hand, all parts of a conductor must become hot when heat is transferred from one end of it to the other. Convection cannot be considered as a form of vibration at all, since it does not represent the transmission of energy from particle to particle of a mass, so much as the change of location of a relatively large amount of heat. It cannot proceed, however, without the aid of either conduction or radiation, inasmuch as the heat given by one mass to another can be received only through the medium of matter or ether. As before observed, ether-borne heat energy is now regarded as nothing more or less than electricity. End of section 7. Section 8 of The Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 4. The Sources of Light. Rising from underneath the world and flooding all nature with the growing splendor of its light, the morning sun has ever been to man a symbol of the power of goodness. The unparalleled poetic imagination of the Greeks clothed this symbolic object with personal attributes, and formulated the fiery chariot and flying steeds of the sun god Apollo, the Baldur of the Norsemen, the Christ of early German legend. A growing Christianity synchronized with the effacement of the personal and divine attributes of light. The 3rd century in Europe saw the development of an established church, Christian, and an established science, Greek. The properties of matter, light, sound, heat, as defined by Aristotle, became the accepted creed of Europe. A science not less dogmatic than theology ruled the thoughts of men until near the end of the 16th century, until Roger Bacon and Bruno and Galileo, with other less illustrious but not less courageous investigators, had suffered contempt and persecution, and even languished in prison for the splendid heresy of experimental truth. The conception of force, intangible, irresistible, indestructible, was long in making its way into any system of popular philosophy. The world, as a cosmos of substance, possessed of varying qualities, was all sufficient explanation for medieval thought of the phenomena of sense and the fabrications of reason. Light, like other things now conceded to be forms of force, was deemed a substance or a quality of substance. Generally, it was held to be a substance, possessed, like other substances, of such qualities as elasticity, reflection, and solubility, absorption. The law of the angle of incidence and reflection was known to the Egyptians and the Greeks. The Assyrians were familiar with the lens. The Arabs imitated from Greece and developed a system of optics involving a knowledge of mirrors, plane and spherical, lenses and prisms, the straight-line propagation of light, shadows and semi-shadows, or penumbra. That light travels in straight lines was one of the articles of faith of the Platonic school. Not all the Greek philosophers, however, maintained this view, and the variance of their opinions foreshadowed the uncertainty concerning light, which has characterized all subsequent discussions of its exact nature. Aristotle wrote more voluminously than any of the Greeks upon this question, but his conclusions are dubious and obscure. Through his influence, the scholastics were led to regard light as something immaterial, rather a quality of bodies than a substance, and they sought to find in the bodies themselves something analogous with the color sensation of the eye. Both Euclid and Plato, however, conceived of light as something projected from the eye upon an illuminated body, causing sight as soon as it met another substance which emanated from the body. Pythagoras and Democritus held that visible bodies projected something into the eye, whereby they became visible. The Greeks knew something of spherical and parabolic mirrors. The story is told of Archimedes that when the Romans were besieging his native city, Syracuse, he defended it by the use of mirrors reflecting the sun's rays, which focused upon the ships of the Romans as they came near, setting them on fire. The terrific heat developed in a modern solar engine makes this tale not so impossible as might at first sight appear, although it is likely that the men rather than the ships of the Romans were the sufferers under the fierce reflection from the mirrors of the Greeks. That the latter had gathered much other evidence with regard to the phenomena of light is unquestioned, for in a fragment of a Greek document discovered in Egypt, mention is made of various familiar optical illusions. They had observed, for example, that a ring on the bottom of an empty vessel, just hidden by the edge, becomes visible when water is poured into the vessel, and Cleomedes observed that in the same way the sun may be visible when it has actually sunk below the horizon. The Greeks had noticed also that the sun appears larger when rising or setting than when high in the heavens. They were familiar with the fact that light glances off from a mirror at the same angle as that at which it strikes. Among the Romans, no investigators of natural phenomena appeared to add anything of moment to the discoveries of the Greeks. Lucretius made some interesting comments on magnetism. Seneca observed and taught the identity of the colors in the edge of a piece of glass with those of the rainbow. He did not explain why they were identical. He remarked that a globular glass vessel full of water magnifies objects, from which he was led to conclude that there is nothing so deceptive as sight, an inference not particularly ingenious nor highly illuminating as an explanation. Abu Ali al-Hasan ibn al-Hasan ibn al-Haytham rose into favor under one of the caliphs of Egypt as a result of a plan, which he never carried out, to regulate the flow of the Nile for purposes of irrigation. He made a study of plane and spherical mirrors, and understood also the principle of parabolic reflectors, such as are used today in searchlights or in the headlights of locomotives, in which all the rays leave the mirror in parallel lines. He knew that a ray of light is flashed back from the surface of water at the same angle as that at which it strikes. He knew also that a beam of light entering water is bent from its course, refracted, to use the modern term. He was aware of the fact of the apparent enlargement of the sun's diameter on approaching the horizon, and correctly explained it as due to the fact that the sun's diameter is then estimated by the size of less distant terrestrial objects, a view admitted by most scientists today. Alhazen, as he is more briefly known, also first described the human eye with exactitude of detail, and originated the famous and difficult problem in optics known as Alhazen's problem. Given the position of a luminous point and of the eye, to find the spot at which reflection takes place on a spherical, cylindrical, or conical mirror. Earlier even than the mirror appears the record of the lens. Among the ruins of Nineveh is reported to have been found a lens of rock crystal. Burning glasses were manufactured at an early date in Greece. In Aristophanes' Comedy of the Clouds is found mention of a fine transparent stone with which fires are kindled, and by which, standing in the sun, one can, though at a distance, melt all the writing on a waxen tablet of the times. From the millennium of the beginning of this era, European thought for 500 years plodded blindly along the road that Grecian philosophy had pointed. Roger Bacon, the one great man in all his time who dared to make a place for original thought and experimental science, was crushed to silence by a 10 years' imprisonment for heresy. Petrus Ramus in Paris was forbidden on pain of corporal punishment to teach or write against the great Aristotle. With Petrus Ramus must likewise be mentioned Franciscus Patricius, a learned Italian, fiercely persecuted by the Aristotelians on account of his heretical theory that light and darkness together produce warmth and cold. From the various theories of the philosophers of Greece, it is evident that the nature of light, even in those early times, was a much mooted question. Previous to the time of Newton, opinions as to its exact constitution were divided. Some held it to be a real substance. Others, especially the followers of Aristotle, considered it a property or quality of matter. Early in the 17th century, Descartes formulated a new hypothesis as to the nature of light. He held that it is neither material nor a property of matter, but a vibration of that something of which matter is composed, its second element. He assumed that the whole universe is filled with minute spheres of this elemental substance. Through the constant motion of the particles of luminous bodies, these little spheres are jarred, and since there is no empty space in the universe beside them, one sphere immediately touching another, this jar or disturbance is immediately distributed in straight lines. As an explanation of this thesis, he compares the propagation of light with the motion imparted to the whole length of a stick when one end of it is pushed. A similar disturbance, in his opinion, may be caused by the eye, from which he explains how cats and other animals whose eyes glitter can see in the dark. Against this Cartesian hypothesis, it has been urged that through these rows of spheres, light would be propagated not in straight lines alone, but in every direction, as pressure is transmitted in all directions by water. Descartes, however, had a large following for a time in his belief as to the nature of light. Later appeared two main theories of light, vis-à-vis the corpuscular theory and the undulatory theory. The former theory was essentially that of the Greeks, although they adorned it with various fanciful hypotheses. The great exponent of this theory in more recent times was Sir Isaac Newton, who based his acceptance of it on the conviction that the rectilinear propagation of light was explainable only on this basis. Sound waves, he argued, may be heard around corners. water waves swing around the jutting point of land, since light travels in straight lines, the great philosopher concluded that it must be due to the projection from luminous bodies of extremely minute particles or corpuscles at a tremendous distance. A contrary view was advocated by Christian Huygens about the end of the 17th century. This famous Dutch physicist regarded light, like sound, as a form of wave motion. A very serious difficulty confronted this theory at the outset. Sound, as is well known, cannot traverse a vacuum. Von Guericke, the Magdeburg magician, had shown some years previously that a clock cannot be heard to strike in a receiver exhausted of air. Light, however, can be seen through such a vacuum without difficulty, and travels without perceptible retardation through the enormous interstellar spaces, possibly vacua, infinitely better than can be gotten by the best means artificially. Some medium, Huygens reasoned, must be there to transmit these vibrations. He boldly assumed such a medium and called it the luminiferous or light-bearing ether. The fact that other forms of undulatory motion, such as sound waves and water waves, can sweep around corners, he did not explain. At first sight, the corpuscular theory of light would seem to be by far the simpler and more obvious explanation of the two, and for more than 100 years the weight of Newton's authority threw the balance in favor of this theory. So many facts opposed to this theory have appeared, however, in modern experimentation, that the corpuscular theory is today practically abandoned. Light is admittedly a form of vibration. Light, it has been said, is a form of vibration, but it is evidently not the same vibration as that which takes place in the molecules of a heated conductor, nor is it the same as the series of condensations and rarefactions of the air that is called sound. These latter are vibrations of matter, and light is evidently a vibration of a different nature, for no amount of light applied to one side of an iron door will shine through to the other side. Heat, on the contrary, or sound, will very quickly be transferred by conduction to the farther side of the door. Light, as it reaches the earth from the sun, must be considered as something closely analogous to radiant heat, if not identical with it. Recent study of the effects of radiation show that light and radiant heat are actually the same. Modern theory regards light as a form of radiant heat, whose wavelengths are such that they directly affect the optic nerve. The great source of light on the earth, far transcending all others, is the sun. It is by no means the only source. The moon, though intermittent in the amount of its light and shining in full radiance for only a few nights each month, must nevertheless be reckoned as a valuable adjunct illuminant to the sun. The light from stars and planets, too, is considerable. Walter Huff, in his Development of Illumination, says, "Under the clear night sky of the Arizona deserts, the atmosphere seems charged with star mist. Eminences miles away may be outlined, the dial of a watch may be read, and a trail followed with little difficulty. These are the conditions under which night journeys are made to avoid the burning sun. The planet Venus," he continues, "at certain times sheds light sufficient for the traveler over open country. There are at times nights of remarkable luminescence. Clouds become phosphorescent, and often under certain states of electrical stress, during high winds, glimmer with a faint light not amounting to a discharge of the electric fluid. Frequently successive flashes of heat lightning aid the traveler in finding his way. It is possible also that the soil over certain regions may become phosphorescent under the light of the sun and retain the property during the night, as certain gems are phosphorescent after being submitted to sunlight. Snow has this property. Gaseous emanations of a phosphorescent character are occasionally abundant enough to produce temporary illumination, and the phosphorescent light of tropical seas has drawn forth many remarks on its beauty. Most of the work in the cities of today is done by diffused light. The direct rays of the sun are found in almost all cases too powerful for purposes of reading or writing, but the diffused light reflected in 1,000 different directions from all surfaces not perfectly black or smooth supplies an abundance of light, soft yet bright enough for use. Since the introduction of artificial illuminants, it has ever been the aim of inventors to produce a light resembling this diffused daylight. The old sperm oil lamps and tallow dips of Europe, which came over with the colonists to America, were there superseded by petroleum lamps. The addition of the argand chimney of glass, the invention of which dates back only to about 1780, facilitated the development of the first really practical artificial illuminant. Even today, this old type of chimney and burner may be seen in the student lamp so popular for reading purposes. The invention of the argand lamp with the brilliantly luminous kerosene soon made nights reading a general practice. Everybody could now read, even the poor, and everybody did. It is an interesting coincidence that is brought out by a recent writer on illumination, Dr. David T. Day, that the progress of the countries of the civilized world today is in nearly every case directly proportional to their consumption of kerosene. The arc lamp, with its incandescent light of Edison, marked a step forward toward the production of an ideal artificial light. But the arc light is not constant, and even when surrounded with a large globe, not sufficiently diffused for reading purposes. The incandescent bulb, notwithstanding the improved tantalum and osmium filaments, gives a glare too concentrated for ease in working. The nearest approach to diffused daylight has been made in the Hewitt mercury vapor lamp, where a small quantity of mercury in a long vacuum tube is first vaporized and then rendered luminous under the influence of the electric current. This lamp, however, is open to objection on the ground of its color. The ideal lamp has yet to appear. End of section 8.
Section 9 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2016. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 5. The speed of light. Among all the properties of light, none is more striking than its speed. Previous to the 17th century, this had always been supposed to be infinite, and the discovery of the gradual propagation of light is one of the most wonderful achievements of that wonderful period in the history of physics, the Renaissance. The first attempt to measure the speed of light was made by Galileo. He ascertained the time for one person to signal with a lamp to another and receive back the signal. The experiment was tried at night when the two observers were close together and again when they were nearly a mile apart. If a difference in time could be detected, then light would travel with finite velocity. Galileo was not able from his experiments to settle the question. About 30 years later, a young Dane, Olaf Rømer, was observing the eclipses of Jupiter's moons. It was noticed that the times of revolution of these moons in their orbits were not the same at all periods of the year and were greater than the average when the apparent size of Jupiter was diminishing. Considering it in the highest degree improbable that the actual motions should be affected with any inequality of this sort, Rømer became convinced that the observed irregularities must be explained on the supposition that the velocity of light is finite. He said that the discrepancy could be accounted for by assuming that it took time for light to come from Jupiter to the Earth. On November 9, 1676, an eclipse took place at 5 hours 35 minutes 45 seconds, while by computation it should have been at 5 hours 25 minutes 45 seconds. On November 9, 1676, an eclipse took place at 5 hours 35 minutes 45 seconds, while by computation it should have been at 5 hours 25 minutes 45 seconds. On November 22nd, he explained his theory to the French Academy more fully and said that it required light 22 minutes to cross the Earth's orbit. The more correct value is now known to be 16 minutes and 36 seconds. Like the news of so many other great discoveries, Römer's announcement fell upon deaf ears. It was 50 years before the scientific world recognized the truth and the value of his contribution to knowledge. Römer computed the velocity of light to be 309,000 kilometers, about 186,000 miles, per second. Subsequent determinations made by astronomers and physicists have corrected this computation but little. The most accurate estimates of this figure are those made by Jean-Léon Foucault, inventor of the gyroscope and originator of the Foucault pendulum in France, and Albert R. Michelson of the United States Navy in America. The speed found by Michelson as the result of more than 100 trials lasting over some 2 months of daily experimentation averaged 299,740 kilometers or 186,300 miles per second. The speed of light in a vacuum is estimated as but slightly greater than in air. The velocity of light in water was a pregnant question in determining the true nature of light. The discussion of this problem belongs to very recent times. It shows what remarkable influence the opinions of Isaac Newton exercised, and illustrates how easy it is even for scientific men to take sides in a discussion where only truth is sought. According to the adherents of the Newtonian school, the speed of light in water, a denser medium than air, should be greater than its speed in air, just as the speed of sound in iron is greater than in wood. But if light be a vibrational phenomenon, the speed should be less in water than in air. This was the fact which the exponents of the undulatory theory, of whom Thomas Young in England and Fresnel, Malus and Foucault in France were the leading lights, were called upon to demonstrate if the Newtonian theory was to be refuted. Foucault took up the idea, constructed a sort of light siren which made more than 10,000 revolutions by second, and reflecting a beam of light showed a deviation of the ray upon a mirror at a distance. This deviation he found to be greater when the ray of light was passed through water, and his experiment gave conclusive proof that the Newtonian theory of light was false. The speed of light in water was found to be just about 3/4 of the speed in air. That light in passing from air through a dense medium, such as water or glass, suffers a retardation was a natural inference. That a distant light gives less illumination than one which is near was early a fact of common observation. The exact extent to which distance would affect the amount of light received, however, is not so generally known. The Earth receives a certain amount of light from the Sun, an amount varying with the latitude and the seasons. At first blush it might seem as if this light would increase in direct proportion to the nearness of the Sun, as if, supposing the Earth was half as far away, the light would be twice as great, and the heat received on the Earth would only be doubled. That such is not the case is now known to every student of the elements of physics. It has been estimated, indeed, that if the Earth were moved halfway from its present position toward the Sun, the whole face of nature would be changed. Life as it now exists would be impossible. No trees, grass, or any verdure would cover the face of the Earth. Water would be unknown, existing only as a prodigious enveloping veil of vapor through which the sun's rays would pass with considerable loss of energy. Enough would be transmitted, however, so that metals such as tin and lead and even zinc would be liquids, mercury a gas, sulfur a boiling fluid mass. An intense glare would illuminate the glowing rocks and naked soil, a light the like of which cannot be conceived by aid of any comparison with the physical world of today. And yet the sun would then be distant more than 40 millions of miles from the surface of the earth. How bright must be the illumination which the sun casts upon the little planet Mercury, so much nearer to him than the earth, it is utterly impossible to imagine. There is no standard of comparison. Yet Mercury is distant 37 million miles from the sun. The sense of perspective is a universal faculty. A ship grows continually smaller in approaching the horizon. A nearby fly crossing the path of vision looks larger than an eagle. A penny held close to the eye will obscure the world. Light, as before observed, travels in straight lines from every illuminated point. From a lighted candle, rays of light radiate in every direction straight away from the flame. The artist familiarly represents the light of a candle by an illuminated circle around it, which rapidly shades from white to dark gray or black shadow. This illuminated circle represents in reality a hollow sphere or shell of light, and each radiant vibration coming from the source of light is spread over the surface of the sphere. It is a well-known fact that if the radius of such a sphere be made to increase, the area of the sphere will also increase, but much faster than the radius, in fact, as the square of the latter. The surface of a 2-inch ball is 4 times as great as that of an inch ball. The surface of a 3-inch ball is 9 times as great as that of an inch ball. Similarly, the light which from a point within would reach the surface of a hollow sphere 1 foot in diameter would be spread over 9 times the same area if the radius of the sphere were 3 feet. Hence, each point on the surface of the larger sphere would receive only 1/9 as much light. The amount or intensity of light, then, varies not exactly as the inverse of the distance, but inversely as the square of the distance from the source of light. In general, as any light wave advances, its energy is being distributed over a surface which increases directly as the square of the distance the wave has traveled. It must be noted, however, that this law of intensity applies only to the direct light from a luminous body, for the total illumination on a given surface is usually very much increased by the light reflected from nearby non-luminous bodies. Hence it is that white walls and furnishings add so much to the total amount of light in a room. The law of the intensity of light is evidently analogous to that of gravity, where it was seen that a pound weight at the surface of the earth, 4,000 miles from its center, would weigh only 1/4 pounds at the distance of 4,000 miles from the surface, 8,000 miles from its center, or twice as far away as at the surface. It is this strangely persistent law of inverse squares which, more than any other fact of physics, points to the ultimate unification of all force under one head. The law holds true for gravity, electric and magnetic attraction and repulsion, light, sound, heat, and so-called radiant heat, together with numerous other less fundamental physical relationships. An ingenious yet extremely simple instrument for measuring the amount of light received from a given source was invented about the end of the 18th century by an American, Benjamin Thompson, afterward Count Rumford. In front of a ground glass screen, he fixed an opaque rod, placing a bright lamp and a candle at such distances from the rod that the shadows thrown by each light upon the screen appeared equally bright. Measuring the distance of each light from the shadows cast, he found the lamp to be 4 times as far away as the candle, from which, by the law of inverse squares, he perceived that the lamp was twice as bright as the candle. Some 50 years later, another light-measuring instrument was produced by the famous chemist Robert Wilhelm Bunsen. This admirably simple device consisted of a sheet of white paper with a grease spot on it. The experiment may easily be made by anyone. If the paper is equally illuminated from both sides, the grease spot will be hardly visible, but if the light upon one side is made ever so little brighter than upon the other, the spot will at once appear on the darker side brighter, and on the brighter side darker, than the rest of the paper. The obvious reason of this is that the matte surface of the white paper reflects back more and transmits less of the light which falls upon it than does the part covered with a film of grease. If now a standard light can be placed on one side of this paper, any other light whose candle power is to be determined may be shifted back on the other side until the grease spot is no longer visible, when by measuring the distances of the two lights from the paper screen, the relative intensity may easily be determined. Incandescent electric lamps, arc lights, and in fact all common illuminants are measured in candle power. One British standard candle power is the rate at which light is emitted by a flame of a sperm candle weighing 1/6 of a pound and burning 120 grains per hour. The amount of light from such a source, however, has been shown to vary as much as 20%, hence the standard is somewhat unsatisfactory. Ordinary electric glow lamps are equivalent to 16 standard candles and are therefore called 16 CP candle power lamps. Other varieties of photometer light measurers have subsequently been invented, one of which, Wheatstone's, produces very beautiful luminous effects. Similar in many ways to the measurement of the light of the sun is the accurate estimation of solar heat. In 1883, Samuel Pierpont Langley invented the bolometer, briefly described as an exquisitely delicate thermopile. Langley's invention was a part of his careful and elaborate preparation for that remarkable trip to the then almost unknown summit of Mount Whitney in Southern California, where the summits of the Sierra Nevada, rising precipitously in the dry air to a height of nearly 15,000 feet over the Mojave Desert to the eastward, furnished a suitable location for the study of the influence of the Earth's atmosphere upon the radiations from the sun. I spent nearly a year, says Langley, before ascending the mountain, in inventing and perfecting the new instrument which I have called the bolometer, or ray measurer. The principle on which it is founded is the same as that employed by my late lamented friend Sir William Siemens for measuring temperatures at the bottom of the sea, which is that a smaller electric current flows through a warm wire than a cold one. One great difficulty was to make the conducting wire very thin and yet continuous, and for this purpose almost endless experiments were made, among other substances pure gold having been obtained by chemical means in a plate so thin that it transmitted a sea-green light through the solid substance of the metal. This proving unsuitable, I learned that iron had been rolled of extraordinary thinness in a contest of skill between some English and American ironmasters, and, procuring some, I found that 15,000 of the iron plates they had rolled, laid one on the other, would make but 1 English inch. Out of this the first bolometers were made. The iron is now replaced by platinum in wires, or rather tapes, from a 2,000th to a 20,000th of an inch thick, all but invisible, being far finer than a human hair. This thread acts as though sensitive, like a nerve laid bare to every indication of heat and cold. It is then a sort of sentient thing. What the eye sees as light, it feels as heat, and what the eye sees as a narrow band of darkness, the Fraunhofer line, this feels as a narrow belt of cold, so that, when moved parallel to itself and the Fraunhofer lines down the spectrum, it registers their presence. Langley's fascinating story of his experimental trip to Mount Whitney, told in the records of the Royal Institution, is full of thrilling imaginative touches. A few lines may serve to show something of the immense difficulties which he had to overcome in getting his results. He writes, We commenced our slow toil northward with the thermometer at 110 degrees in the shade, if any shade there be in the shadeless desert, which seems to be chiefly inhabited by rattlesnakes of an ashen-grey color and a peculiarly venomous bite. There is no water, save at the rarest intervals, and the soil at a distance seems as though strewed with sheets of salt, which aids the delusive show of the mirage. At last, after a seemingly interminable journey, we pitched our tents and fell to work, for you remember we must have 2 stations, a low and a high one, to compare the results. And here we labored 3 weeks in almost intolerable heat, the instruments having to be constantly swept clear of the red desert dust which the hot wind brought. Close by these tents, a thermometer covered by a single sheet of glass and surrounded by wool rose to 237 degrees in the sun, and sometimes in the tent, which was darkened for the study of separate rays, the heat was absolutely beyond human endurance. Finally, our apparatus was taken apart and packed in small pieces on the backs of mules, who were to carry it by a 10 days' journey through the mountains to the other side of the rocky wall, which, though only 10 or 12 miles distant, arose miles above our heads. And, leaving these mule trains to go with the escort by this longer route, I started with a guide by a nearer way to those white gleams in the upper skies that had daily tantalized us below in the desert with suggestions of delicious, unattainable cold. That desert sun had tanned our faces to a leather-like brown, and the change to the cooler air as we ascended was at first delightful. But the colder it grew, the more the sun burnt the skin, quite literally burnt, I may say, so that by the end of the 3rd day my face and hands, case-hardened as I thought in the desert, began to look as if they had been seared with red-hot irons, here in the cold, where the thermometer had fallen to freezing at night. And still, as we ascended, the paradoxical effect increased. The colder it grew about us, the hotter the sun blazed above. It almost seemed as though sunbeams up here were different things, and contained something which the air filters out before they reach us in our customary abodes. Radiation here is increased by the absence of water vapor too, and, on the whole, this intimate personal experience fell in almost too well with our anticipations that the air is an even more elaborate trap to catch the sunbeams than had been surmised, and that this effect of selective absorption and radiation was intimately connected with that change of the primal energies and primal color of the sun which we had climbed toward it to study. We suffered from cold, the ice forming 3 inches deep in the tents at night, and from mountain sickness, but we were too busy to pay much attention to bodily comfort and worked with desperate energy to utilize the remaining autumn days, which were all too short. Here, as below, the sunlight entered a darkened tent and was spread into a spectrum which was explored throughout by the bolometer, measuring on the same separate rays which we had studied below in the desert, all of which were different up here and having grown stronger, but in very different proportions. The delicately constructed bolometer of Langley has been brought in comparatively recent years to very high perfection, so as to record a change of temperature of 1/10,000,000th of a degree centigrade. Professor C.B. Boyes in 1888 constructed a similar instrument capable of indicating so minute quantities of radiant heat that in the absence of atmospheric absorption, the heat radiated from a candle 2 miles away would be distinctly registered. A still more perfect instrument lately completed in America, similar to the radiometer of Dr. Crookes, reached a marvelous degree of sensitiveness to radiant energy. Experiments were made on the heat of a candle situated 2,000 feet from the concave mirror which focused its rays upon the instrument. The feeble radiations of the candle at this great distance sufficed to turn the indicator through nearly 100 scale divisions, and even the face of an observer, when placed in the position before occupied by the candle, produced a deflection of 25 scale divisions. as a tenth of a single scale division could readily be observed, it will be seen, to speak figuratively, that with this radiometer one might note the approach of a friend while yet some miles distant, merely by the glow of his countenance. End of section 9.
Section 10 of the Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 6, Reflection and Refraction, Part 1. A strange phenomenon of light, which long puzzled the scientific world, was that of polarization, or two-sidedness. A crystal of tourmaline held between the eye and a light source will appear transparent. A second crystal, placed in front of it, will also allow the light to pass as long as the two crystals are held lengthwise. If one of them be turned at a right angle to the other, the light is cut off. The explanation of this was a hard nut for Young to crack. He cracked it thus. It is possible, he wrote in a letter to a friend, to explain in this undulatory theory a transverse vibration propagated in the direction of the radius and with equal velocity, the motions of the particles being in a certain constant direction, with respect to that radius, transverse to the ray, and this is polarization. Thus Young explained that what happened in the progress of a light ray is the same thing as that which happens in the progress of a water wave. A stick of wood may be seen to rise and fall with the waves, but it does not advance with them, for the vibration is transverse to the direction of propagation. The apparent motion of the water in a wave is a forward motion. The actual motion is up and down. So it is with light. The analogy may be carried further. For when the wave approaches the shore, the lower part of it is arrested and the upper part is still carried forward by the impulse from behind. The result is that the wave now takes a downward as well as a forward motion, and this effect becoming more and more pronounced, the top of the wave curls completely over the water below and crashes as a breaker on the shore. In light, this change of direction also takes place whenever the light wave passes from air to a denser medium, such as water. If a ray of light strike the water at an angle, the lower part of the wave being arrested at the surface of the water, the ray bends downward into the water. A normal, or perpendicular to the surface of the water, would therefore form a larger angle with the ray in the air than in the water. The ray is said to be bent toward the normal in passing from a rare to a denser medium. Imagine the same ray to be shot back again, and it will obviously be bent from the normal as it leaves the water. It is evident from the water wave analogy that the more the wave is stopped at the surface of the new medium, the greater will be the bending. In a substance like diamond, where the light travels less than half as fast as in air, the bending is very great, and the colors of which the white light is composed are much scattered and broken. Hence appear the magnificent lights in the diamond. In crown glass, where the wave travels 2/3 as fast as in air, there is less stoppage and consequently less refraction of the ray. In water, as has been remarked, the speed is 3/4 of the speed in air, hence the bending is still less. Owing to this bending downward of a ray of light, as it enters the water, it is evident that an observant trout will sight a fisherman some seconds before the latter sees the trout, and in the same way, the setting sun will be visible to a fish in the water as shining apparently some degrees above the horizon. The effects of refraction are interesting, sometimes startling. It has been noted above that a ray of light passing from water into air suffers a bending away from the normal to the surface. That is, it tends to lie down and run along the surface. This tendency is more marked as the angle of incidence increases. When the ray of light strikes the undersurface of the water at a long angle, it does not pass into the air, but runs along the surface of the water. Increase the angle ever so slightly, and the ray is actually bent down again through the water, affording the striking phenomenon of total reflection. A familiar example of total reflection is found in the mirage. This reflection may take place whenever a ray of light passes from one layer of air to another of different density. The image of an inverted ship is observed commonly enough at sea before the ship itself comes over the horizon. The images of distant shores may be seen in the like manner. The rays of light from the ship pass upward and reach some stratum of air which is warmer and consequently rarer than the air above the water immediately surrounding the vessel. From this rarer medium, the image is bent down by total reflection and projected to some distant point. In the sandy plains of Egypt and other hot countries, a similar phenomenon is due to similar causes. In this case, however, the image formed is reflected from a cooler stratum of air than that immediately above the burning sand of the desert. The inverted picture of trees, thus formed in the sky, is precisely analogous to the reflection of trees on the shore of a still lake. The reflecting medium in both cases is denser than that surrounding the object. As the amount of light varies inversely as the square of the distance from the source, so also it varies with the angle at which the light falls. If the rays are projected vertically upon a surface, the amount of light will be greater than that received when they reach the surface at an angle. Hence the amount of light, as well as the amount of heat, which reaches the polar regions, is far less than that which falls upon the equator. The same amount of light is spread over a larger surface. Anything like accurate measurement of the amount of light received upon an object must always take into account the light due to reflection, for every visible surface reflects. If it did not, it would not be visible. The scattering of the rays which results from a rough surface is utilized in minimizing the glare from a too brilliant source of light, such as the incandescent mantle of the Walsbach gaslight or the dazzling core of the electric arc. Ground glass globes enclose the lights and diffuse the intense brightness by scattering the rays which pass through the roughened surface. The great difficulty from an economic standpoint with this method of softening the radiated light is that nearly half of the illuminating power is wasted in the resistance offered by the semi-opaque glass globe. Diffuse reflection takes place at all points of the roughened surface. The famous mirror maze, composed of several mirrors at various angles and scores of panes of clear glass, is so confusing that even extreme watchfulness will not prevent the observer from running into a pane of glass, not being able to perceive it. The reflection of any object in a plane mirror is a virtual, not a real image. There is no actual image where the object appears to be, and the virtual image so formed will be exactly as far in the rear of the mirror as the object itself is in front of it. This would follow inevitably from the well-known law of reflection, which, so far back as the time of Archimedes, was well understood as a fundamental principle of all mirrors, of every shape and description. If two mirrors are placed so as to touch at right angles, a candle placed in the angle will show three images reflected, no matter how the observer stands. By making the angle of the mirrors continually smaller, more and more images will be brought into view. When the angle of the mirrors is 60 degrees, the angle of an equilateral triangle, 5 images will appear, and 7 if the mirrors are inclined at an angle of 45 degrees. When the angle is made small enough so that the mirrors are almost parallel, the number of reflections becomes practically infinite. An interesting and striking fact with regard to these multiple images is that every image so formed, as well as the luminous object itself, will lie on the circumference of a circle of which the juncture of the mirrors is the exact center. This again may readily be shown to be an obvious result of the familiar law of reflection. Sir David Brewster of the University of Edinburgh invented early in the 19th century a reflecting instrument through which he became better known than by any of his more elaborate contributions to science. The kaleidoscope, a simple little device to be had today in almost any toy shop, was constructed by him with 3 plane mirrors. These were made of equal width and length and fitted into a tube closed at one end by a disc or plate of ground glass, behind which irregular bits of colored glass or porcelain were allowed to tumble and turn in any direction. The latter were held in place by another disc of clear glass. When viewed from a small aperture in the farther end of the tube, these bits of colored glass showed by their multiple reflections in the three mirrors an amazing variety of beautiful symmetrical designs, apparently without number or end. So great at one time was the demand for these kaleidoscopes that it was found impossible to supply it. A more complicated series of images of great diversity is made by placing 6 mirrors together so as to form a regular hexagon, each angle of which is exactly twice the angle of an equilateral triangle, or 120 degrees. This is the form of which mirrors have been combined to produce the remarkable vistas of crystal mazes, of which a noteworthy example has recently been constructed in Paris, wherein a turn of a lever transports the observer from a forest grove to the interior of a Hindu temple or the wonderful Arabian palace of Aladdin. The image formed by a glass mirror is not reflected by the glass. Back of each such mirror will be found a thin layer of some metallic substance, which forms a much better reflecting surface than the glass. A beam of light falling on the mirror will be partly reflected from the front surface of the glass, but mainly from the metallic hinder surface. Thus it becomes apparent why a mirror, especially a thick one, forms 2 or more distinct images of an object seen at an angle in the glass. A consideration of the law of total reflection will show how many such images may actually be formed, reflected back and forth from the 2 surfaces of the mirror, and growing rapidly dimmer, so that usually not more than 1 or 2 are plainly seen. A certain astronomical observer, not many years ago, betrayed in this connection an unconscious vein of humor. By means of the reflections from a plate of clear glass, he announced the discovery of a large satellite circling the planet Venus. On account of these repeated images in glass mirrors, they are usually replaced in physical observatories by metallic reflectors. The great law of reflection, that the angle of the incident ray equals the angle of the reflected ray, was found to hold true for all angles and all surfaces. The law applies with equal rigor to a plane mirror or to the reflecting surface of any other type, spherical, cylindrical, conical, concave, or convex. Nearly 1,000 years ago, the famous image problem of the Arab Al-Hazen, to which reference has already been made, was formulated, calling for a proof of the images formed in plane, spherical, and conical mirrors. The spreading of the rays of light will obviously change the appearance of the image formed in any convex reflecting surface, while the opposite effect will produce an opposite change in the image formed in a concave reflector. The image formed by looking in the bowl of an ordinary spoon is seen to be inverted, no matter which way the spoon is held, sideways or upside down. This will always be found true, unless the spoon is large and brought very close to the face. Looking at the back of the spoon, however, the image is seen to be erect, no matter how near or far away the spoon is held. The reason is easily seen. Every ray of light from an object must glance off from the polished metallic surface at the same angle as that at which it strikes. In a concave surface, such as the hollow of a spoon, these rays must evidently meet somewhere and then cross. Evidently, the image formed after they cross will be upside down and left side right. Such an image is real, for it is actually formed where it appears to be, and in this respect differs from the images formed in plane or convex mirrors, which apparently exist where experience proves they cannot exist, namely, behind the reflector. If the reflection in a concave surface is made by an object held close to the mirror, it will form an enlarged, erect visual image. The rays of light do not pass through the focus or crossing point of the mirror, hence there is no inversion, and the image, but for the enlargement, is exactly like that formed in a plane mirror. It appears behind the surface. Parabolic mirrors which have come into such great use for powerful lighting purposes, as for example, in the headlights of automobiles and locomotives, show but a slight modification of the concave spherical mirror. The change, though slight, is important, for all the rays of light from the lamp within the reflector now strike the sidewalls at such an angle that they pass out in parallel lines. Therefore, except for the light lost in absorption, at the metallic surface, every bit of illumination is centered in the one direction. The illuminating power of these reflectors, when furnished with a brilliant light, is enormous. The parabolic mirror is said to have been known since the time of Archimedes. The convex surface of the back of an ordinary spoon forms, as has been said, an erect image, which appears reduced and at a distance of several inches behind the spoon. Withdraw the spoon slowly, and the image continues to recede and diminish, until at a certain point, diminution seems to stop, and the image remains constant no matter how far away the spoon is moved. Here, as before, a converging point of the rays of light will be found, this time behind the mirror. But there will be no crossing, for the rays will exactly meet, and the image be reduced to a point only when the object has been removed to a distance theoretically infinite. In general, it has been said of all real images that they are those formed by the reflected rays themselves, whereas virtual images are formed by their imaginary prolongations. The real image is always inverted and the virtual image erect. By analogy with the phenomena of images in convex and concave mirrors, the process of image formation through the ordinary convex lens will readily be understood. The process here, as has been shown, is one of refraction, not of reflection of light. But the bending of the rays to a focus on either side of the lens will determine, as before, the form of the image, whether erect or inverted. Images formed by refraction through a convex lens must in all cases, when the object is outside the focus, be real, since the figure is actually formed and may be shown on a screen exactly where it appears to be. If the object is placed inside the focus of the lens, for example, between the focus and the lens itself, an enlarged virtual image will be seen. This is the case in ordinary reading glasses. The light rays from all extremities of the object, letters or whatnot, under examination are twice refracted by the double convex surface of the lens, and the eye sees these points of the object along the line last traveled by the light. Hence the object appears greatly magnified, its extremities appearing to be much farther apart than in reality they are. The more convex the lens, the greater is its magnifying power, but the greater, at the same time, the difficulty in using it without some correction of the spherical aberration, which increases with the curvature of the lens. Double convex lenses, used as magnifying glasses, are frequently called simple microscopes, as distinguished from the powerful compound microscope, which by the aid of brilliant illumination produces an image many thousand times larger than the original. The focus of all convex lenses was seen to be the place where the rays of light, traveling straight to the lens, are bent together by refraction and meet. There will evidently be two such foci formed, one on either side of every double convex lens. These are the so-called conjugate foci of the lens. In concave lenses, there is no real focus possible, since all rays will be refracted in a direction away from the perpendicular through the center of the lens. All images through such a lens will therefore be virtual images. End of section 10. Section 11 of the Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 6, Reflection and Refraction, Part 2. The earliest lenses were made in Europe of rock crystal, although lenses of glass appear to have been known to the Greeks. The lenses of Hans Lippershey of Middelburg, the inventor of the binocular telescope, were made of rock crystal. These small instruments, it is interesting to note, sold at that time, 1608, for the large sum of 900 gulden. Galileo's lenses, one of them concave, the other convex, were made of glass. Sparing neither expense nor labor, he succeeded in constructing an instrument which magnified an object nearly 1,000 times and brought it more than 30 times nearer. He went to Venice to display his telescope. Many noblemen and senators, says he, although of great age, mounted the steps of the highest church towers at Venice to watch the ships, which were visible through my glass, 2 hours before they were seen entering the harbor. In the early telescopes, lenses were made with very great focal lengths, the beams converging in some cases at a distance of 10, 20, 30, 40, and in one instance of 123 feet from the center of the lens. These lenses were mounted on high poles, and being unprotected by a tube, gave very inferior results. The purpose of these great clumsy objectives was the avoidance of the color dispersion, which is always observable at the edges of a simple lens of pronounced curvature, since the prism has shown that the blue rays of light are bent more than the red. They must come to a focus behind a lens a little sooner than the red rays. This is the explanation of the fact that so many common lenses, reading glasses, etc., make it appear that the objects behind them are surrounded by a colored halo. This is more noticeable in lenses of much curvature, for the difference in focus between the red rays and the blue is then emphasized. Leonhard Euler suggests that lenses made out of 2 different materials of different refractive powers would probably cure this chromatic aberration. He tried to produce such a lens, but failed. A London optician, John Doland, taking up Euler's idea, began a series of tests in making lenses which were achromatic, for example, showing no color dispersion. Years of repeated failure in this direction were finally crowned with success, and Doland produced a lens made of crown and flint glass, which was perfectly free from color and entirely accurate. His accomplishment created a sensation throughout Europe and greatly facilitated from that time the growth of astronomy. Lenses began to increase in diameter and telescopes in size. Herschel, the discoverer of the 2 inmost moons of Saturn, added immense concave mirrors to his telescopes, whereby the light gathering power of the instrument was vastly increased. At Parsonstown in Ireland was completed a gigantic reflecting telescope with a mirror 6 feet across and a tube 58 feet long and 7 feet in diameter, so that a certain ecclesiastic, Dean Peacock, once walked through it with uplifted umbrella. The achromatic lenses which made possible these great telescopes were likewise instrumental in the development of microscopes, to which they were early applied. The first microscope was constructed in the beginning of the 17th century by Zacharias Johannides, a Dutch optician. The eyepieces of his microscope were made at first concave. Subsequent improvements made both lenses convex. Spectacles were also manufactured with achromatic lenses, greatly increasing their comfort and serviceability. The inventor of spectacles must rest his claim to this honor upon an inscription dated some 300 years before the invention of achromatic lenses. Upon the tomb of Salvino Armato in Florence is carved below the bust of this noble